Imam. Jeste, proći tebe, jer se želim sutra.
Good morning, everyone. Welcome to the second day of EEM 2023. I hope you had a good rest last night. So let's continue with our work today. I now invite the members of the working presidency for today's first session to take their seats. Professor Svetlana Pelemiš, University of East Sarajevo, Faculty of Technology, Zvornik. Professor Marion Florian, National Research and Development Institute for Cryogenic and Isotopic Technologies, Romania. And Professor Stevan Armakovic, Department of Physics, Faculty of Sciences, Novi Sad. Let's welcome our guests, our distinguished members of the working presidency.
Dear guests and participants, thank you very much for coming to the second day of this very important and interesting event. It gives me an immense pleasure to announce Professor Dr. Zoran Petrovic from the Serbian Academy of Sciences and Arts. We will start this second day of conference with the lecture on topic Physical Foundations of Non-Equilibrium Plasmas as the basis for technologies ranging from nanoelectronics to plasma medicine and plasma applications in agriculture. Let's greet Professor Petrovic.
Before we start, I will just say a few words about Professor Petrovic's very large biography. Zoran Petrovic obtained his Bachelor of Science and Master of Science degrees at Faculty of Electrical Engineering, University of Belgrade, and his PhD at Australian National University in 1985 in atomic and molecular physics. He has been employed at the Institute of Physics, University of Belgrade from 1978 till 2019, where he became a research professor in 1995. Currently, Zoran Petrovic is affiliated with Serbian Academy of Science and Arts and has been professor of plasma physics from 2020 to 2022 at Ulster University, Jordanstown, United Kingdom, where he continued being affiliated as Professor Emeritus. He founded and led Laboratory for Gaseous Electronics and has been the head of the Department of Experimental Physics and principal investigator of the Center of Excellence on non-equilibrium processes. He has published 300 papers in international journals, co-authored one book, and gave more than 100 invited lectures at international conferences. He also supervised or co-supervised 20 PhD students. Zoran Petrovic has had postdoctoral sabbaticals at several laboratories, including JILA Boulder, USA, San Diego State University, Keio University, Japan, and he was a visiting researcher and professor in many laboratories around the world. He is a fellow and distinguished referee of the APS, both lifetime awards. He has been elected to the Serbian Academy of Sciences and Arts in year 2000, where he has been secretary of the Department of Engineering, Applied Sciences. He has received the leading national awards, Nikola Tesla for technological development and Marko Jaric for physics. Zoran Petrovic has been on editorial boards of PSST, EPJD, EPJTI, and more. He was one of the organizing committees of most international conferences on low temperature plasma physics. His scientific interests range from atomic and molecular collisions and transport, physics of swarms and charged particles, automated analysis of the swarm data, gas breakdown, plasma modeling, diagnostics and control of low pressure up to atmospheric pressure plasmas, positrons in gases and in human tissue, to numerous plasma applications, including plasma processing of integrated circuits, plasma medicine, and plasmas for agriculture and food industry. Let's give a warm welcome to Professor Petrovic.
Well, welcome to the spring. I think we entered spring just a few hours ago. Okay. As you can see from my title, and as it will be definitely obvious from my lecture, I like my plasmas and I like them to be in non-equilibrium. And I'll try to explain why. Also, as you could see from my biography, fundamental studies and applications went hand in hand. And I'm always trying to make a point that some of the finest fundamental results that I obtained were inspired by people from the industry coming and saying, we have this problem, and vice versa. Some of our fundamental useless results somehow creeped into applications, and I'm proud of that. Okay. I turned it off. Okay. 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 Well, just to see what the difference is between equilibrium and non-equilibrium, and whenever it is mentioned, you see this diagram. To the left, at the low space charge, where is laser? Okay. To the left, you have non-equilibrium plasmas where electrons are really hot and ions and atoms are at the room temperature. And when they are in equilibrium, they are all at the same temperature. So let's take a quiz. Who would like to have medical procedure by equilibrium plasma? This is around 3,000 or 4,000 Kelvin. So you would have to, it will kill all the bacteria, viruses, everything. Somehow, good, bad, doesn't care. Your cells would become very useful for energy, but you don't want to put your hand into it. Oh, sorry. Oh my God. We are developing this kind of plasma because this is at room temperature. At 40 Celsius, we start killing human cells. That is thermal necrosis. So we cannot have any application in medicine where gas will kill the patient. However useful it may be for the goal, whatever that may be. So we are trying to make this kind of plasmas, and also it's easy to make them at low pressures. I'll explain later. But another quiz, I can make them at low pressures, let's say 1 torr or 1/10 of a torr. Would you like to be submitted to 1/10 of a torr in a vacuum vessel? No, I don't think you would. Anyway, so we have to make it at atmospheric pressure with atmospheric combination of gases and add few things here and there if we need them, and make it non-equilibrium. And that's very hard to do, actually. And it has become a thing in the last 20 years. Before that, there were only 2 sources operating at atmospheric pressure, giving you non-equilibrium. An important thing about equilibrium plasmas is if you develop a scientific conclusion produced as some sort of equation, it becomes the law, let's say Saha equation. It works for all equilibrium plasmas. It's like, you know, carved in stone, delivered by God. However, if you deal with non-equilibrium plasmas, they're very much like Tolstoy's unhappy families. Each non-equilibrium plasma is very specific, has its own characteristics. I was trying to pronounce idiosyncrasies, but I thought I would fail, so I did. So anyway, they are all unhappy on their own. And therefore, you have to be Sherlock Holmes for each and every non-equilibrium plasma. So you have to be really motivated to study them, and motivation stems from applications. Let me skip this one. But where lies the beauty? In the eye of beholder or in non-equilibrium? Well, all beautiful things are in non-equilibrium. Can you imagine Niagara Falls in equilibrium? Everything at the same level. A lake. Can you imagine tornadoes in equilibrium? Not even a light breeze. You know, dead sails, ship is not moving. That's equilibrium. Of course, the source of all life is in non-equilibrium. Not just because it's hot here and not so hot there, but because sun is at 6,000 degrees at the surface, and when you take off from the surface, just a few kilometers up, it has millions of degrees in corona. And what we get comes from corona. All these players, whatever. So basically, every non-equilibrium is an opportunity either for beauty or for application. And all applications stem from non-equilibrium, like this one, which Tesla observed as a chance for electricity. Okay, how do we explain that? Well, we pull it to pieces. And we say our non-equilibrium plasmas consist of yellow blocks, red blocks, and there are blue blocks. We have explained it. Okay. It's just like saying you humans consist of carbon, water molecules, a little bit of nitrogen, a little bit of this and that here and there. I explained humans. I explained teenage behavior. I explained complicated diseases. I explained everything just by saying what it consists of. That's humans are non-equilibrium systems, the ultimate non-equilibrium. And I always claim that I study non-equilibrium plasmas as the simplest possible paradigm that I can explain that can be used as a model for more complex things, even teenage behavior. I have 5 grandchildren, just about one has become teenager, other 4 will soon. I will have plenty of studies to do. Okay, because just by saying red, yellow, and blue blocks cannot explain a robot made of Lego blocks, whatever this contraption is, it needs a different level of phenomenology. And although I am atomic and molecular physicist, I can tell you, and I did tell you on the last slide, all these blocks that non-equilibrium plasmas consist of, electron-molecule collisions, blah, 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 blah. It's not enough. I need to tell you a story which is given by a different language. And that language is language of complex nonlinear systems. Language of swarms of particles, language of strongly coupled plasmas. That is needed as a basis. Okay, I will not go into explanation. I will just give you some examples of possible equilibriums. You have equilibrium, but not plasma in equilibrium, not in thermal equilibrium. When you have electric field, charged particles gain energy from the field, lose it in collisions, and they maintain their energy. They are in equilibrium, but that is not local thermodynamic equilibrium. That is non-equilibrium plasmas. But it doesn't change. And then sometimes everything changes from the initial or from the starting positions. Everything relaxes, changes, and it's non-equilibrium in non-equilibrium, in a state of flux. And sometimes we use that. And sometimes you say, okay, when this universe cools down, everything will be in equilibrium. Yeah, thermodynamic equilibrium. This is this temperature. At the moment, it is around 4 Kelvin or 3 Kelvin, I forgot. It will be 0.001 Kelvin eventually, and everything will be in thermal equilibrium. No, it will not be. Why? Because you will have freezing at a very low temperature. This is not an equilibrium situation, because you freeze the structure, and due to the lack of external energy, you cannot change it. So you can ask me, okay, how can I get energy in this frozen universe? Well, if you have a vessel flying, no light, no suns, nothing, eventually you will come close to some dead star, which is sitting there frozen. Here you have star, there you have nothing. It will accelerate you. and your meter for acceleration will press against some surface, and you can put piezo stuff there and power up your very carefully built computer, that you can start your computer again because of the gravity. Gravity is external. It is non-equilibrium system. So eventually universe will be in thermal equilibrium, but it will still be a non-equilibrium system. Oh, just a second. Yeah. Let me build. Now, this is a model of initial universe, which was the only time when everything was in local thermodynamic equilibrium. And then when you add gravity to it, what happens? You have stars and galaxies forming. Now we learned that actually you first formed a lot of black holes, and your universe becomes a very non-equilibrium place. So you have all sorts of different equilibriums, and I like very much this built-in connectivity. If you have C and H, they have built-in Lego shapes, which will make polymers, complex molecules out of C and H, and can be basis foundation of life. Just by the basic chemistry of C and H. And that is what we are trying to squeeze in plasmas. How do we explain it? Well, there is this Boltzmann equation. I will not try to explain this, but it is a complex equation. This is integral differential equations, 3 degrees of freedom here in velocity, and in spatial coordinates, you have 3 degrees, and there is time. So you have 7 degrees of freedom. If you want to have 100 points for very rough calculation, you need 10 to the 14 memory of 10 to the 14. Do you have computer with 10 to the 14 in memory? No, you don't. You cannot solve it. So you have to play with different symmetries. You have to be clever. I will not dwell on that. One important thing is Boltzmann committed suicide. His successor committed suicide. So one gentleman who wrote a book on kinetic theory said, okay, Boltzmann, I forgot who was his successor who committed suicide, but he said, okay, they committed suicides, and now it's our turn to study kinetic theory. Okay. Well, I'm still alive. And one thing that helps me a lot is actually Monte Carlo. I like to gamble, and by the way, Monte Carlo is not solving Boltzmann equation. It is simulated nature. It's simulating nature, producing results which should be identical to that of Boltzmann equation, but it is not a solution. It is independent simulation process. And we do a lot of that too. Sorry, this is Monte Carlo. Again, we actually have to solve integral differential equation for probability of collision to find the time of next collision, but okay, we can do that. And when we do that, we can play with our inputs, which are cross sections, which are probabilities of different collisions. For instance, in argon, you have momentum transfer, you have metastable excitation, you have ionization, a very simple model. And I have plotted 2 distribution functions, which are produced by Boltzmann or Monte Carlo, doesn't matter, with mean energy of 2.44 eV. Both. Could anything be more different? Now, Maxwell-Boltzmann is stretching all the way to very high energies. How can it be? Because in Maxwell is for thermodynamic equilibrium, which means that walls are at the same temperature. So when you suck up energy from the walls, there should be a source of energy, keeping the temperature constant at the walls. So basically, you have infinite flux of energy into the system. And here, you just turn on the field and you tell them, this is your monthly wage. If you spend it on big things, you will have nothing. If you spend it on little things, you will do a lot. Imagine small country entering European Union, saying, I throw all the caution to the wind. I want to be a big spender. Free medicine, retirement funds, infrastructure. And as long as those people do not notice that you are sucking up EU funds, you are okay. When they discover it, then your distribution goes bang. And this is what we play with. We are making mixtures of gases in order to, say, make more of ionization, because Maxwell-Boltzmann will give you a lot of ionization or less of ionization if we need to make atmospheric pressure discharges. And this is one of the tools. And actually, sometimes Boltzmann equation gives you high energy tail larger than Maxwell-Boltzmann. So there are very rich small countries that don't need EU funds to be very, very rich and spend a lot of money. They just have to make that money. And anyway, okay. Another way to do non-equilibrium is through relaxation. You have initial conditions at some moment or at some point, and you let them relax to your final state. But if you have time-varying field, you will have puff, puff, puff. Your mean energy will go up and down, never fully relaxing. And by playing with these terms, you can, actually, this is representation of relaxation. Very early times when you have these Frank-Hertz oscillations. If you know what Frank-Hertz oscillations are, there was a Nobel Prize given for these. We made much nicer plots, but we didn't get Nobel Prize. I don't know why. Maybe we came 100 years too late. But we now know how to play with this and get something for nothing from that. Okay, one important thing is, let's start. Now, this is 100% of energy. Initial energy is 100%, and you are in the field. Actually, you are accelerating, but you're at the 100% of the available energy. And after a few collisions, you will develop several peaks. And after a lot of collisions, you will develop tail. And after a while, you will have nothing at the peak and only a tail. And this is normal discharge. But there are discharges where this peak is maintained because it enters the region where there are no cross sections. Let's say there is region where you have no losses, you cannot lose energy, and they can accelerate further and further. And thank God for that, because otherwise nobody would be hit by lightning, because there would be no thunder, no atmospheric discharges. And if it's true that they induced initial race to produce organic molecules, then there would be no life. So discharges which are not completely relaxed, but which have combination of a relaxed tail and the front, which is at the high energy, which gets accelerated and accelerated, they are very important, for instance, in atmospheric discharges. And in something else, which I will try to explain later. Okay, let's look at another relaxation. We turn off the plasma. We turn it off with walls, that is the black thing, and without walls, infinite plasma, that is the red thing. In your distribution function, with walls suddenly develops a hump at the high energy and the minimum here. because of the shape of cross-section, where electrons which find themselves here can easily run to the walls and be eaten by walls. So this is a major loss. And because of that, basically, your mean energy can start at 6 and go up to more than 7 during relaxation. And that is something that you can play with. But when you have infinite, is this thermodynamic equilibrium, where I have plotted Maxwell-Boltzmann distribution, which is this purple line, and infinite distribution, which is this blue line. It looks like it's the same, but actually at high energies, where you have those huge losses, you will eat up all the electrons with that energy, and you will have no big spenders there. Okay. Now we have to control the charge. Why? Well, for instance, how do we make microchips? We make one electrode, the other electrode, and play with the discharge so that it develops a certain structure close to the walls called double layers, which accelerates the ions to the surface. Ions in the middle are, as we said, at very low energy. It's basically at room temperature, but close to the walls, they get 200 electron volts, and 1 electron volt is 11,000 Kelvin. So 200 electron volts is quite a lot of effective temperature if you can talk about temperature. And that's how we make microchips. Okay, but if you want to make atmospheric pressure breakdown for medical purposes, your growth of charges will be very quick because ionization coefficient is proportional to the density, and basically it number of charged particles will explode in very short time. When you have a lot of charged particles, ions and electrons will have Coulombic force, which will distribute electron energy to ions. They will get heated, and then they will collide with atoms, and they will heat the atoms. So you will go to that right-hand side of that plot with temperatures, and everything would be at the same temperature. You will be in local thermodynamic equilibrium. And in order to make atmospheric pressure discharges, we have to control the growth of charges. For instance, one control is to put in dielectric barrier. So when you produce a lot of charge, it hits the glass over the electrode, produces field, which stops further production. Or you have corona, where you have field which is very high, close to the peak of needle or something, of wire, but further away, it's very low field. So you have very small region with high enough field for multiplication. You can also play with gas mixtures and things like that. I already mentioned runaway breakdown, which is important in lightning. Okay, this is our device, which is atmospheric pressure discharge. We make RF plasma in glass tube in a flow of pure rare gas, because breakdown voltage is small. If we wanted to do it in atmospheric gases because of oxygen, we would put much more voltage. That voltage would be converted to current, and you will have thermal plasma there. So we produce non-thermal plasma, and this is the edge of the tube, and we shoot it into the gas where it interacts with gas molecules and produces a lot of reactive species. So basically, this atmospheric pressure plasma looks like that lightsaber from Star Wars, doesn't it? Yeah. So it's something really fundamental if it comes from Star Wars. But actually, when you look at that plasma in time-resolved manner, you will have these little discharges, and then you will shoot a plasma bullet out. This is a self-propagating system of charges which produce their own field, which multiplies them and propagates them without any external field here. Thanks to that phenomenon, we have life on Earth. So basically, it's not lightsabers that are important, but it is the ordinary bullets in Star Wars, which are actually the true essence of whatever is happening in plasmas. Okay, and now we want to do something. We want to do plasma etching to make chips for your telephone or to make memories for your computer, things like that. Okay, we have electrons that we want to control. Then we produce ions, molecules, photons. We control all these parameters. We make a certain distribution of charges. All of these things have to be controlled, doesn't matter in details. All is there to assure that interaction with the surface goes the way we want it. And it seldom does. I apologize for this. I realized last night that I don't know how to turn off this animation of slides, which, okay, these are two of our sources. This is inductively coupled plasma, just a single coil, making plasma in this glass tube. And this is capacitively coupled plasma with two parallel capacitors producing plasmas. This is used more for etching dielectrics. This is used more for etching semiconductors and also for cleaning surfaces and depositing and cleaning photoresist and whatever. Sorry. Okay, now if we have thermal plasma, our etch profile would be you cut deep, but you undercut in both directions as much as you cut in the perpendicular direction. Not a very good way to make a well. You can make well by throwing a bomb. It would be a deep well, but it would be much wider than deep. So if you get to the water level, you will get a little pond, but not a really useful well for drinking water. We want a well because we need to limit the structures to put more of them on a single chip. So we need to actually have plasma here, ions at zero energy practically, electrons at high energy, and field which is slowing down electrons and accelerating ions so they come straight down at the right angle and hit the bottom of the well. And that's how we make integrated anisotropic, integrated surface by anisotropic etching. Problem, and you see how it really looks. Now this is 20 years ago, so we have actually now at least 20 interconnects of dielectrics, which are used to connect different transistors. So very complex structures. For billion transistors, you have maybe 100 billion connections at 20 different levels, and you have to drill holes through all this. So transistors are made in two steps at the bottom, very easily made, but interconnects. This is one example, for instance. We make etching by putting in pure hydrogen. This is with organic polymer as dielectric. And you see that you have this isotropic etch. You undercut as much as you cut in. If your mixture is not perfect, you will have redeposition, deposition at the bottom, but at the right ratio of 85% of nitrogen to 15% of hydrogen, you have perfect etch. And you have perfectly etched surfaces. Okay. However, when you etch, you put ions on the bottom and they produce a field which eventually stops ions and makes undercuts called notching. This is our simulation of notching. This is actually observed. we extended the simulation and proved that actually the only thing that you can do is get 1:7 aspect ratio. So 7 times the width of the well would be the depth of the well. At the moment, your telephones have aspect ratio of 200. How did that come about? Not this way, even though I thought that this temporal turning off and on would be the way to go. We tried 2-frequency etching to control the distribution function better. And we did, I will not go into details. Some people did it much better than we did, and actually they made monoenergetic beams. But then I proposed something by looking at DC discharge. And normally your discharge starts at the cathode and has exponential growth towards the anode. This is production of electrons. However, at higher fields, you have peaks closer to the cathode, and actually they begin to dominate. This is because ions which are produced also get accelerated. Now they cannot ionize or excite with the excitation, but they can produce fast neutrals like billiard balls. And after one collision of ion with molecule, you have very fast neutral. And these fast neutrals shoot with the same energy. And we proposed fast neutral etching. You can see the Doppler profile. If you put one electrode to be made of graphite, you have no reflection of these ions. However, normally you have fast neutrals going towards the electrode and being reflected from the surface because they got neutralized and they are going back. So we have made proof that it is by fast neutrals. And this is actually simulation of a real device. Electron exponential growth. You have neutrals multiplying towards the cathode. When it's all combined, it fits experiment very well. And if you have a grid here, which is 50% transparent, then here in the region where you have no field, you still have excitation and ionization. Your beam of fast neutral is going through and exciting the gas. Oh my God. This is the basis for fast neutral plasma etching. And this is how your telephones are made now with resolutions of 5 or 6 nanometers. Okay, I will not go into positrons. And I will just tell you a few words about plasma-induced chemistry. We did very complex simulations involving 59 species, 1,000 reactions. Now we have 100 species and 2,000 reactions. And we can now actually calculate, for instance, how small amount of humidity in the air would change. And these are the ions that we want in reaction with living matter, with cancer cells, for instance. And we can change their fluxes by a factor of 1,000 and even more, much more. But this is useless science, so you should not pay attention to it. This chemistry is very non-equilibrium. Each process is independent, producing a single channel. And because it's not equilibrated by a large number of collisions, you can control production of each and every species. And you can play with conditions and see which conditions would give you maximum of, let's say, O2 plus or H3O plus, or things like that. We make primary comparisons with ions, because ions sampled in our mass analyzer from the plasma are those which were made in the plasma. Neutrals coming are modified by our ionizer in the system. So we rely on the model for neutrals much more than on mass analyzer. But we have control of that, and I will not go there. And how can we apply that? Well, we can hit cancer cells. This is control, and we can kill them. And we checked, and it's apoptosis, which is what you want. Our colleagues from France were allowed to make experiments on living organisms, and you can see that actually they succeeded in reducing from this dark blue to this red size of tumor. This blue would be control group, and this is with plasma radiation, and this mouse is much better off, though it still has cancer. But it's very hard. It's easy to apply plasma to surface cancer, like melanoma, and it has been applied. But internal cancers, oh. And then a new paradigm kicked in, which is we treat water with plasma, fill it with reactive molecules like H2O2, produced by plasma, superoxide, all these things, nitric or one of these nitrogen acids, and we pump them into the not just water, but medium, and put it in the human. And then we realized that actually you can, and they're trying now to teach your immune system to kill your own cancer cells. It usually doesn't do because they are your cells. So they are freezing and thawing cancer cells to extract from them something called lysate. So don't ask me anything in Latin. I just reproduce sounds like 2-year-old. I have no idea what it means and how to pronounce it really. So these lysates are built into dendritic cells, which bring the information to T cells, and they fight the fight. Anyway, if you treat everything by plasma, things become much more optimal. Now, this is what happens if you actually apply. Now, our plasma-treated medium is actually very, very strong, and it starts killing healthy human cells in high doses. But at 25% or 50%, it's not really that dangerous, but it still kills more than 50% of cancer cells. So this is much better than freeze-thaw technique, and we have proposed plasma treatment as a way to go for plasma-induced immuno vaccination of cancer. And basically, to control these things that you put into your medium, you have to do all these non-equilibrium plasma chemical models. And I will not go there. This is just something that I wrote down on paper at 2 a.m. this morning. I think it was already spring, or may have been still winter, so I was slightly off balance. These are things that we did. We played with plasmas on textiles. We played with plasmas with positrons instead of electrons. We played with plasmas for wound healing, for methicillin resistive whatever bacteria is. And we had actually, in all these aspects, we had good success. And I could give you another page or two with successes that we had, and 10 pages with what we tried and didn't work. So basically, I tell my colleagues, hit it with plasma, see whether something happens, and then we decide whether we can get something out of it. And this is what we do. And it has to be non-equilibrium. Thank you. Sorry, I took more of your time, but I think start a bit later.
Thank you very much, Professor Petrovic, for giving us an insight how plasmas can be practically applied. We all enjoyed. I'm sure that the audience has a lot of questions for Professor Petrovic. We have a time for 1 or 2 questions. So I'm opening the questioning session.
Inductively coupled plasma, also hydrogen plasma reduction, but for me it's very interesting your first slide about introduction. You have relationship between temperature and density, and unit for temperature,
Charge particle density, yes.
yeah, is electron volt. And why not Kelvin? Is mistake or?
Electron volt is the same as Kelvin. 1 electron volt is 11,600 Kelvin.
Okay, okay.
I prefer to say electron volt because I don't believe that non-equilibrium systems have temperature to speak of.
Okay, okay.
It's not a temperature. We often apply term temperature to plasmas, but it's never a single temperature. Even in the local thermodynamic equilibrium plasmas, it's not real temperature, it is a fitting parameter. So I prefer electron volts because it's a mean energy, and then it tells me where to tweak my cross sections to get certain response.
Because at this diagram, no values. And
Not all the values are there. 1 EV is 11,000 Kelvin.
no values for this x-axis, y-axis, because this is for me some.
Okay, let's see that later. I don't want to bother the whole
Okay,
auditorium.
thank you very much.
Going to the first slide.
Okay, thank you.
Do we have more questions for Professor Petrovic? I would like to ask you to give us just one small example of plasma application in agriculture.
Yes. Actually, we didn't start with medicine, although we wanted, but our medical doctors were. So we had very good interaction with people from Siniša Stanković Institute, and especially people from plants department. So we were able to increase the sprouting probability from, let's say, and of course you cannot apply that for maize or wheat. But for very rare endangered species that have 2 or 3% probability that the seed will grow, if we increase it to 90% probability, it is a big thing. So
yes,
that's one thing. Yes. Another thing was Nevena did some work. I was not really involved. They had kali, which they activated by plasma and sealed it off in something that can be dissolved by water, and you throw it into the soil, and it grows like a seed, artificial seed.
Great. Thank you very much, and let's give an applause for Professor Petrovic. So right now I'm using the opportunity to once again mention that this is a hybrid event, meaning that some lectures will be given online. So the next lecture is going to be precisely online, and it will be given by Professor Dr. Monica Magureanu, and the topic of the lecture will be plasma treatment of polluted water.
Monica Magureanu is a scientific researcher of the first degree at the National Institute for Lasers, Plasma and Radiation Physics. She graduated from the Faculty of Physics at the University of Bucharest in 1996 and was employed in the institute in the same year. From 1999 to 2002, she completed her PhD studies at the Institute for Low Temperature Plasma Physics, INP Greifswald, on the investigation of microwave plasma for the conversion of methane into higher hydrocarbons. She returned to the Institute in 2002, started her experimental work on plasma chemistry and plasma catalysis, and became scientific researcher of the first degree in 2009. Her research interests in the field of plasma physics and plasma chemistry are mainly related to non-thermal plasmas generated in electrical discharges at atmospheric pressure for environmental applications, gas and water treatment, as well as plasma treatment of seeds and plasma treatment of various materials for diverse applications.
Thank you very much for the introduction. Can you hear me and can you see the presentation?
Yes, we can see you and we can hear you loud and clear.
Ah, perfect. Okay.
Thank you.
Okay, so I'd like to start by thanking the organizers for giving me the opportunity of this talk. As you already heard, I will talk about plasma treatment of polluted water. And I will start with a short introduction on water pollution, especially on contaminants of emerging concern and advanced oxidation processes as solution to this problem. Obviously, I will skip the plasma basics because it was this great lecture of Professor Petrovic, so there is no need for me to say anything else. But I will show a few reactive species that are formed in plasma in contact with liquid. And then I will move to the results on the degradation of organic contaminants in water by non-thermal plasma. And here I will focus on plasma reactor design and operating conditions. And I'll have only one slide on the degradation mechanisms and pathways. And then the greatest challenge in plasma application is the upscaling and, of course, the cost of the treatment. And in the end, I'll say a few words on the safety of the plasma-treated effluent and the possibilities for water reuse. So it is now common knowledge that water contains various pollutants. Among them are the contaminants of emerging concern. They can have harmful effects on aquatic species and also on human health, but they are not yet regulated under the current environmental legislation. And an example are the pharmaceutical compounds. And in this picture, you see the main sources of pharmaceuticals in the environment, the human medicine and the veterinary medicine. So after consumption, the excreted human pharmaceuticals end up in wastewater treatment plants. There they are partly removed, but not completely. So they can be found also in the effluent, and then they are discharged into the environment. Another possibility is for the pharmaceutical to be absorbed on the sludge. The sludge is sometimes used as fertilizer, so then they firstly contaminate soil, and then by runoff and leaching, they reach surface and groundwater. In case of veterinary pharmaceuticals, the manure is again used as fertilizer, so again there is soil contamination. Or in case of aquaculture, the pharmaceuticals are directly discharged in the water. And from the environment, they come back to us either in fish or in crops irrigated with polluted water, or in animals that have consumed the crops or the water. Or we can get them even in drinking water if they can still escape the final treatment step in drinking water treatment plants. There are also other sources, but less important than these two. And of particular concern are the antibiotics that are not only toxic, but also contribute to the spread of antimicrobial resistance in the environment. So it would be great if we could treat the water, for instance, the hospital wastewater, And like this, we could reduce the load on the wastewater treatment plants. So as I said, the wastewater treatment plants can reduce to some extent the pollutants, but they cannot eliminate them completely because they were actually not designed for this purpose. And for this reason, other techniques, such as, for instance, advanced oxidation processes, have started to be investigated. They are aimed at the production of hydroxyl radicals, either by using oxidants such as ozone or hydrogen peroxide, or by combining them with catalysts, or introducing also UV light or ultrasound. So the idea is to generate these OH radicals, which are highly reactive and non-selective. So they can react basically with any organic compound and degrade it to small fragments, or even produce complete mineralization, the complete degradation to carbon dioxide, water, and inorganic compounds. The most well-known AOPs are catalytic ozonation, this combination of ozone and hydrogen peroxide, the Fenton process, photocatalysis, and so on. And among them, the youngest, I can say, is non-thermal plasma that uses only electrical energy and is able to produce OH radicals and also a number of other oxidants in situ without needing any external additives. In all these processes, there are several key parameters that we have to look at. Of course, the removal of the target pollutant, the mineralization, as I said, complete degradation to CO2, water, and inorganics, and also the energy efficiency, which is defined as the amount of pollutant that is removed per unit of energy spent in the process. Okay, I'm skipping the plasma basics, and I just want to show an example of the species that can be formed in plasma in contact with liquid. This was an example with plasma jet. So we have electrons, we have ions, positive and negative ions, we have radicals, molecules, and so on. They can all penetrate inside the liquid on a smaller distance or a longer one, depending on their properties and depending on their reactivity. And at the interface and also in the bulk liquid, they can react with the pollutants and degrade them. So it is important in the degradation to have a good transfer of this species from the gas, from the plasma to the liquid. And now I'll show a few plasma reactors from very simple ones, such as this DBD, where the liquid to be treated is placed in a vessel between the electrodes, and it's separated by one or two dielectric barriers. So the discharge is generated in the gas and is in contact with the liquid. There are then corona discharge reactors, either in needle-to-plate configuration or in wire-to-plate configuration. So as I said, in order to improve the transfer of the species, it is important to have a high surface-to-volume ratio. And for this purpose, such configurations with a thin layer of water have been investigated as well. For instance, this one, the DBD with falling liquid film, where the water to be treated flows as a thin film on the surface of the inner electrode. Or this configuration, which is a bit more exotic, where there is a rotating drum taking the liquid and transporting it here to the plasma zone. Another way to increase the surface to volume ratio is to produce the discharge inside gas bubbles, or to have droplets of liquid passing through the plasma zone, such as this, this configuration that I'll show you later some results. It was done in a group in Estonia, and they patented it as well. Or another possibility is to reuse or recycle the effluent gas from the plasma by bubbling it through the solution in a tank. This configuration we have used a long time ago. And we observed that this gas bubbling, the gas recycling, reduces significantly the time needed to eliminate the pollutants, and also increases considerably the energy efficiency or the energy yield. And this is the configuration that we are using now. It is a corona discharge in wire-to-plate configuration with an array of several wires as the high voltage electrode. The discharge is initiated at the wires and then propagates towards the surface of the liquid. The water is circulated continuously between the plasma reactor and this solution reservoir. And the gas, the effluent gas from the plasma that contains a lot of ozone, is bubbled through the solution here. And these are some results obtained for methylparaben, which is not a pharmaceutical, but it's a preservative. So as you see, by plasma alone, we need 60 minutes to completely eliminate this pollutant. But with the gas bubbling, we can reduce this time to only 10 minutes. And there is also a significant improvement in mineralization. And in order to explain this, we had a look at some of the species that are formed in the plasma. The OH radicals, their concentration is almost 2 times higher when using plasma ozonation or plasma gas recycling as compared to plasma alone. And on the other hand, the hydrogen peroxide concentration decreases significantly. So what happens is that the ozone generated in the plasma and the hydrogen peroxide also generated by the plasma react, and they form extra OH radicals besides the radicals that are already formed in the plasma reactor. So this explains the large increase in the efficiency. Now going to the operating conditions, an important parameter is the initial concentration of the pollutant. Usually in the literature, milligrams per liter to hundreds of milligrams per liter have been studied. This is, of course, orders of magnitude higher than what is found in the environment, and also much higher than what we can find in wastewater. But it is useful to have such large concentrations in order to see the degradation on a measurable time scale, and also in order to be able to look at the degradation product. In plasma, generally, the degradation obeys a first-order kinetics. So as you see, the decrease in concentration is exponential. And something else that is observed is that with increasing initial concentration, the degradation is slower. However, although the degradation is slower, for the same treatment time or for the same input energy, the amount of pollutant removed is much higher for the higher initial concentration as for the lower one. So the efficiency is obviously higher. And an obvious fact is that the treatment of contaminated water should be done at the source of pollution. We shouldn't wait until it goes to the river or lake where it is already diluted and the volume is very high. There, the plasma would not stand a chance. but we can treat the water, for instance, at the hospital, where the volume is lower, the concentration is higher, and this can be done successfully. Another important parameter is the input energy. So obviously, with increasing input power, the concentration of active species increases, and the degradation of the target compound will be faster. This is an example obtained in a corona with liquid shower that I showed you a few slides ago. So with increasing input energy, the time needed to reach a certain level of degradation is significantly reduced. However, this is not always beneficial from the point of view of energy efficiency. As you see, there is a significant drop in efficiency with increasing power. So there is always a balance between the time needed to eliminate the pollutant and the cost. Another important thing is how we deliver this energy. These are some experiments that we've done in our pulsed corona with different pulse durations from 50 to 400 nanoseconds. And we observed that reducing the pulse duration actually reduces the time needed to degrade the pollutant. Actually, there is an optimum somewhere. If we plot this as a function of input energy, we observe that the process is much more efficient for shorter pulses. And the difference in efficiency can be even 1 order of magnitude. In order to explain this behavior, we had a look at the most common active species that are formed in the plasma. For instance, the ozone, we observed that the ozone is in the gas phase is produced much more efficiently for shorter pulses. And we explain this by the increase in temperature and in water vapor in case of long pulses, which are both detrimental to ozone formation. The hydrogen peroxide was not affected by pulse length. And in case of OH, again, it is formed in a more efficient manner for short pulses, probably due to a recombination to hydrogen peroxide in case of longer ones. Now, a few words on the degradation mechanism. This is an example for beta-lactam antibiotics, amoxicillin or ampicillin. And these are all the degradation products that have been obtained in the literature. As you see, there are quite a lot of them. There are several pathways for the degradation. For instance, we have hydrolysis of the beta-lactam ring to give this product, or we can have hydroxylation, or we can have oxidation here at the sulfur atom, and so on. So, as I said, there are many degradation pathways until the molecule is fragmented to smaller and smaller pieces, and finally mineralization can occur. However, mineralization is quite a long process, and it's also very energy consuming. So it would be good to know where to stop along the way. So on the one hand, we don't spend so much energy, but on the other hand, we need to make sure that the effluent is environmentally safe. This is why it's important from a practical point of view to look at these products, because some of them can be toxic as well, or can be even more toxic than the parent compound. So it's good to know when to stop the treatment. Now, as I said, upscaling is one of the biggest challenges in plasma applications, and there are very few reports in literature on pilot scale plasma reactors. These are 2 of them. For instance, this one, it's a corona in point-of-plate configuration over a relatively thin layer of water, was developed by a company in the US, the AquaPure, and they used it to treat real wastewater or spiked surface water contaminated with pharmaceuticals. And their conclusion was that the operational costs are similar with the other advanced oxidation processes, with ozonation, actually. Another example is this Corona with liquid shower that I told you before. So it's similar to an electrostatic precipitator. They have wire-to-plate Corona, and the water to be treated is passing through the plasma zone as droplets or jets. And again, they used it at pilot scale to treat hospital wastewater. Now, regarding the costs, the energy yield or the energy efficiency in the literature ranges between milligrams per liter and hundreds of grams per kilowatt hour. Sorry. So it's orders of magnitude between them. And in order to optimize the process, we need to maximize the production of active species, and also to maximize the mass transfer of the active species from the plasma to the liquid. Now, in this real wastewater, the one that I showed you before with the shower, the authors obtained 0.5 gram per kilowatt hour for paracetamol degradation. In the same device, the same authors obtained 20 gram per kilowatt hour in distilled water. So it's more than one order of magnitude difference. And they say that the difference is due to the difference in concentration, and not because of the water matrix, not because in real wastewater, paracetamol is also accompanied by many, many other pollutants. And we did also look at mixtures of pharmaceuticals. For instance, this mixture of amoxicillin, diclofenac, and ibuprofen. We looked at them in mixtures and in monocomponent solution. And surprising and encouraging result was that actually in mixtures, the pharmaceuticals degrade faster, or at least in this one. We're still struggling to understand why in a satisfactory way. But anyway, this does not apply to the mineralization, which essentially depends on the theoretical oxygen demand, so on the amount of oxygen needed for complete mineralization. Now, a few words on the safety of the treated effluent. Toxicity there can be given by residual target compound, also by the target, by the intermediates of the degradation, and sometimes also by oxidizing species that are still remaining in the solution. This is an example where the toxicity is shown by the inhibition and luminescence of the Vibrio fishery. And the authors used here quite an efficient reactor that is completely eliminating the pollutant, norfloxacin in this case, after only 1 minute of treatment. So as you see, there is a decrease in toxicity in the beginning, but then as the toxic byproducts are formed, there is again an increase, and only after long treatment time, there is again a decrease in toxicity. And in case of antibiotics, another important thing is to eliminate completely the antibacterial activity, because otherwise bacterial adaptation can still occur, and again resistance can develop. And a few words on water reuse. We've done some experiments with a herbicide, 2,4-dichlorophenoxyacetic acid. As you see, it is degraded after 20 minutes of plasma treatment. The mineralization is much slower. And then we looked at tomato seeds watered with these solutions. And as you see here, for short treatment times, when the pesticide is still present in the solution, the roots are quite small and they're obviously ill and the plants don't develop normally. But as soon as it was completely eliminated, the roots are and the plants are similar with the ones irrigated with clean water. This is seen also in this graph. We have also looked at the uptake of this pesticide and its degradation products in the plants. And we observed that for treatment times that are sufficiently long after the pesticide is eliminated, then it's not found in the plants as well, and also its degradation products are absent in the plants. So, of course, some more tests should be done, but this is one small first step to the reuse of polluted water in agriculture for irrigation. So thank you very much for your attention. I'd like to acknowledge the projects that are funding our research and our collaborations. And if you have questions, please ask.
Thank you very much, Dr. Maguranu, for your wonderful presentation. And thank you for showing us how plasmas can be applied for the treatment of water. This is extremely interesting, especially for me and my research group. Do we have questions for Dr. Maguranu? Yes, please, doctor. Stop it. Set.
Monica, thank you very much for very interesting and important presentation regarding treatment of wastewater, because reuse of water is very important for us. I have two questions. Firstly, regarding upscaling, you used this carbon electrode, and for this advanced oxidation process, you use O3, hydrogen peroxide, gaseous oxygen. Did you ensure CO2 emission in your process? Because you know, in last time we have always to say something about CO2 emission. This is first question. Second question, because I'm a metallurgist and we worked treatment of wastewater in order to remove iron and other elements. Of course, this is not topic of your presentation, but you said mineralization. If you say mineralization, which metals are focused? Iron or something other, titanium? Because this is very important results if you can make some mineralization. Thank you very much.
Okay, thank you. So first of all, about the CO2. No, first things first. The filled reactors were unfortunately not mine, but yes, they used this corona about liquid or corona with droplets for the bigger reactors. Some CO2 can be observed. In our lab scale reactor, we used CO2 as a measure for the mineralization when we did not have the total organic carbon analysis to make the carbon balance. So yes, some CO2 is observed. But as I said, it would be anyway too expensive to reach CO2. So probably the treatment process should be stopped sometimes sooner, when in the water there are still some small organic molecules, but which are harmless, and they can be eliminated by other means. Regarding the mineralization, mineralization is the complete degradation of the organic compound. So in order to obtain from it only CO2, water, and inorganics, and usually inorganics will be in ionic form. So I don't expect it, we will get a metal out of it. It will be, for instance, sulfur dioxide or nitrogen dioxide, nitrates. Hope this answered your questions.
Thank you very much, Dr. Maguranu. And let's have an applause for Dr. Maguranu.
Thank you.
So we are continuing the conference program. The second invited lecture for today will be given by Professor Dr. Stevan Blagojević. The topic of his lecture will be the 21st century, the age of zeolites.
Where he finished his primary school and secondary grammar school. He graduated from the Faculty of Physical Chemistry in 1993 and completed his master's degree in 1996 and his PhD degree in 2010. Since 1993, he has been employed at the Institute for General and Physical Chemistry, where he went through all the positions from research intern, research associate, head of laboratory for detergents, deputy director. Since January 2016, Dr. Blagojević has held the position of the director of the Institute for General and Physical Chemistry. In his work so far, Dr. Blagojević has published 45 papers in SCI listed journals and given over 100 talks at conferences and seminars. His work has had 280 citations with the H index of 10. He is a member of the Serbian Chemical Society and the Society of Physical Chemists of Serbia. Apart from his regular activities at the Institute, Dr. Blagojević is also a lecturer at the Department for Chemicals of the Ministry of Environmental Protection of the Republic of Serbia for obtaining the license of an advisor for chemicals, and he is an associate for many companies in the area of chemical industry in the region. Let's give a warm welcome to Dr. Blagojević.
Thank you very much. Thank you very much. It's very great pleasure to be here after so long years, because I served the Yugoslav People Army here in Sarajevo, and it was here in this hotel on skiing in Rajska Dolina. It is here, like 100 meters. So it is very nice to be here, and in the name of the Institute and my personal name, many thanks to Professor Dragan that called us from Mr. Dvornik, and special greetings for all Institute to our head, Professor Paja, who was 10 years president of our president of the board of directors for Institute. So now I will So first, as you know, thank you very much for coming. My lecture will be about zeolites. You will see first a few words about Institute that I am member 30 years. Institute of General Physical Chemistry has been founded 62 years ago in May 1961. Presently, Institute of General Physical Chemistry performs fundamental research in the area of complex compounds, chemistry, biochemistry, biophysics, and in the last 10 years in a food chemistry, because we recognize that everything will be a food chemistry in the next 10 years. There will be no other chemistry than food chemistry and biochemistry. Yes, in the next 10 years, here, be sure. It will be the chemistry in the multinational companies, like Henkel, like his chemistry. But this chemistry will be biochemistry and food chemistry. First of all, few words about science. As you know, science, everybody thinks that it is something easy, but it is not. First is Robert Hyman, everything is theoretically impossible until it's done. So we must know that in this 21st century, we have a lot of doubts in science. One of the main doubts is theoretical science or theoretical chemistry or physics good enough, or it must be done by experiment. We in Institute of General Physics or Chemistry are fully experimental science. We do all experiments, simulations, and other computer things we don't do at all. 62 years ago, and of course, in this 21st century, because all of this internet and everything, science is in some problems. Everybody can talk about science, everybody can talk about everything. So I please all of you to believe in science as one of the greatest collective endeavors of humanity. And of course, at the end, one word of Isaac Newton, keeping in mind that always what we know is a drop, what we don't know is the ocean. That is Isaac Newton many years ago. So you will see we are in the job of zeolite for, I don't know, more than 30 years, but everything that we know about zeolite is a drop. And ocean, we'll see what is. The applied research in our institute is comprised of chemical detergents, silicates, aluminosilicate, food processing from laboratory. That is our main advantage, from laboratory research to pilot plants up to do big plants, as you'll see. All that research leading to our technologies about purified filter production, regenerative devices, detergents, zeolites, compact detergents, copolymers, bleaching activators, hydrate dissolving, granulating zeolites, and so on and so on. The main business in the last 2 years was with company Birch. Now it's Alumina, and if they are here, I don't see many good works for them. That detergent zeolite we make with them with patent in 1982, and in that time all production was exported to European countries like Henkel, Procter & Gamble, England, Spain, Turkey, and so on. After that, the second thing is that we make capacities for liquid glass. After that, white fillers, it is for the rubber for tires. After that, rubber white fillers and granulated zeolite, all was before this war and what's going on in this transition, all was going abroad to export. After that, we have a company in Italy, Zeolite Mira in Venice. It is a small place, Mira, near to Venice, with detergent zeolite production with Benkiser, Henkel, Mira, Lanza, liquid water glass, and copolymer production. You will see after the copolymer is the product that must go with the zeolites in detergents, and all was exported. So we know in Institute, we know very good that distinction between experiment, good result, and what is the main thing, industrial application. Good result, good experiment is everything. But if our industry said it is good, if industry said it is, we can make it by this precision more and more and more, then it is good. Then it is right chemistry. Nowadays, 62 years after all these problems, we have about 50 employees, PhD, Master of Science, and Bachelor of Science in physical chemistry, biochemistry, biology, and technical science. I must just one more thing. Institute of General Physical Chemistry in Belgrade University, physical chemistry separated faculty from the first year. It was a part of Faculty of Science, but it started from the first year. It is the group that is different from chemistry. It is not a part of chemistry, it is only in Belgrade. So we have a lot of physical chemists. And from the foundation, we have the following laboratories: boundary phases, that is the detergent lab, chemical laboratory with all analytical techniques, electrochemical laboratory, one of the, I think, best in all ex-Yugoslavia, thermal analysis laboratory, biochemistry, biophysics, NMR, Engen, spectrochemistry, materials, and in the modern time, material science and hydrogen energy lab, because we saw that hydrogen energy will be in the next years will be in advance. This is one of things that not more people know that big Soviet Union gives to big Yugoslavia only 2 Lenin Prize. One was for President Tito, and the second is for us. In 1982, by the decree of Leonid Brezhnev, these younger people don't know, but Leonid Brezhnev was I don't know, king. He gave us a Lenin Prize to the Institute for outstanding results and success for developing scientific operations and creating better life for USA and Yugoslavia. And in that time, it was the diplomatic protocol when an institution have a Lenin Prize. In that time, it is signed by ambassador, because ambassador represents Soviet Union. But we have signed of Brezhnev, it is something more. After that, just to see one more thing, in 1992, Professor Vucelic from our institute get Theodor Schweikert Prize for Zero Light and Detergents Investigation. It was by Colloid Society, belongs to all the scientific societies in Germany, founded in 1992 in Leipzig. Just the names. First name, Miloš Josef Švuger, Henkel. Second, Professor Vucelic, Institute of Physics. Third, BASF. Third. Fourth, any research. After that, Rubinsky, Henkel, VFK, it is the institute in Germany, it is part of Henkel Institute for Detergent Germany. After 30 years after us, Institute of Physikalische Chemie in Köln. This is the only thing that Germans are 30 years below us, below any part in Serbia. 30 years before us, and from Free University Berlin in 217. If you read surnames Schwuger, Horn, Bogatella, Rubinsky, Schollmeier, Stey, Miller, you see that Professor Vucelic is the only one that is not a Jewish. You see, no, it is not at all. Not at all. This part of science, colloid science, detergent science, Jewish science. It is they found that there is a money in that. That is detergents, cosmetics, boundary phases. They found there is a money in that. So just look. During the surnames, you will be after that. After that, we have a lot of prizes. Nikola Tesla Prize. After that, UNDP Prize for Climate Innovation or something like that. This is one of our products from my biochemist. It is from diabetes. It is metabolic product with 2 components that help to people who have a diabetes. We have a special site about that. About you can see on the site. Having in mind the science in history and chemistry more than 60 years, we have more than 150 publications per year in SCI index, in SCI journals. The main fields are physical chemistry, biochemistry, material science, biophysics, colloid chemistry, nonlinear dynamics, food chemistry, food processing technology, with the high impact factors, and 15 scientific projects from Serbian scientific grants. 15 scientific projects here. This is one of our business to remove oily waters, to remove treatments of oily wastewater by using domatic sorption filtering materials. We have tested in Termoelektrana Kostolac, Termoelektrana Zrenjanin, Petrochemia, Pančevac, Saurat. After that, we have a business with drinking water treatment, removal of arsenic, manganese, iron, organic matter. In Elemir, it is a part of Vojvodina with a very big problems in mineralogic, so the water is problematic in Elemir, and remove organic material from wastewater, mercaptans. The main business is detergents of Institute. The main business is detergents. We have analysis of liquid powder detergent, surface tensions, emulgation power, formability, viscosity, irritability. You must know that it is these are pure physical chemistry, because surface tensions, as far as we know, it is true that everybody worked that students exercises on physical chemistry. But when you go to some institute, they said, okay, no, we will make only active butter or something. So we do a pure physical chemistry analysis of detergents. And of course, we use recommendations of IKV, that is German Cosmetic Regulatory and Detergents Association. That is samples of some analysis. That is sample how we test detergents, color care detergents. Will be the difference in color before and after zero detergents. Will be a spot or something like that. This is some of our other business. We have a lot of business with pharmaceutical industry. I, as a physical chemist, did not know that the same component, for example, this serotonin hydrochloride. Serotonin, it is a drug for MAO inhibitor for schizophrenia. It doesn't work if it is not in the crystal, in some crystal rotation. When you put analysis in HPLC, everything is same because water dissolve it, and you have result that it is good. It is clean, but we must do XRP analysis to see the diffraction analysis. I didn't know that some forms, crystal forms, does not work in the brain at all. No, zero effect. Also, we have a electronic microscope and some other. This is some samples of Grinica for our friends in Birac. After that, we have a lot of instruments, infrared spectroscopy, SEM micrographs. That is our biggest business, surface activity, contact angles between, for example, for industry, it is very important, contact angles between glue and glass or plastic. If it's not a good contact angle, this will go up. Just go up, go down. And the problem is when you put, people from science don't understand the numbers. When you put, for example, 60 million of beers by day, if you have a 60 million of this going out, you will be in a big problem because you must solve it. That is contact angle between water droplet and for the printed surface for some, I don't know, some beers, I think so. This is also instrumental method SEM analysis on the surface, chemical analysis of surface. After that, we have ionic chromatography, 2 ionic chromatography with very good response for analysis of anions and cations. And of course, GCMC, this is for analysis of perfumes. It is one of our, big business to have analysis of reference perfumes and perfumes that are imported after that. You see, are they the same? And of course, DSC TGA analysis, DTA and TGA, very good DTA and TGA we have. And XRD, very good XRD. Why XRD? Because all these destructive techniques have a big problem. All destructive techniques will say this is only copper. It's copper. No. You have a copper oxide, you have copper oxide. You can do it only with good XRD and of course good people. Of course, we are the only one in the region that have AdBlue certifications from VDA. As you know, AdBlue is something new, some 10 years ago because of this diesel engines. Now it's going to automotive. It was only big trucks before, but now it's going to automotives. We have only 96 points by Germans, and now we have certification to do analysis of AdBlue. We have a collaborations with CERN since mine 218. 2 of our people is in CERN, Switzerland. And the task is aging, I don't know what their physics, aging for ion detectors cells because implied deposit accumulation, corrosion cranking, I don't know what is that, but this looks like very good. And in this moment, we have a contact with Military Technical Institute from ex-Yugoslavia and Serbia, NAGDI. NAGDI is a company of Saudi King. It is a cosmetic company, one of the biggest in the world. Cosmetic pharmaceutical company, you can see their sites from Kingdom of Saudi Arabia, CERN, Henkel, Zelchem, Birac Alumina Zvornik, Ecolab, the biggest company in the world of detergents for industrial. Belinka, the biggest company in ex-Yugoslavia, chemical company, of course, from hydrogen peroxide, peroxide acids, and something like that. Hermann von Stadler from Germany. Hermann von, you know that it was a Serbian Hermann von, after that Stadler by Hermann von, now it's Hermann von Stadler. Biochemia from the first day, Dieter Tuzla from the first day, from the ex-Yugoslavia, from Tito's period, Ahold Delhaize, Dalia, the oldest company in ex-Yugoslavia, in cosmetic company, Albus, Novi Sad, you know, Boho and everything, Novohem Shabac. We have EU projects, COST, Erasmus, and scientific from IDEA projects. Now we are going to zeolites. Zeolites are using enormous branches of chemical industry. They are versatile materials. A range of applications of chemical industry is million. They are crystalline, almost silicates with a power structure and modified that can be modified by suit various applications. Of course, because of internet and everything, zeolites have a lot of misunderstanding. Normally, people do not recognize that there are synthetic zeolites and natural zeolites. And some people write that natural zeolites can cure cancers and something like that. So the zeolites have a problem like all other in modern knowledge and modern internet, that everything can be used for everything. And of course, that is not true. In 20th century, last century, the zeolites was used in detergents and catalysis. And in the 21st century, we spend in all parts of chemical industry. There are a lot of expectations. There will be leading absorbents, catalysts. They will play a role in agriculture to improve soil quality, increase crop yields, and absorbing a slowly release nutrients. Of course, carbon dioxide absorption, very, very important thing from industrial emissions, and of course, detergents as well. The first thing, zeolites and detergents, that we was, I would say, pioneers with Birch, pioneers in the world. In 19 detergents builder, zeolite is detergent builder, and the purpose of zeolite is to soft the water, and give alkaline to water to detergent. The first is silicate, triphosphate, and after that, tripolyphosphate was recognized as environmentally not good because of rivers and because of phosphate in rivers. And after that, zeolite was with triphosphate, and in about 1980s, triphosphate was banned, as you know, because of rivers and the fishes. And from 90s, zeolite A carbonate and co-builder. That is a copolymer that you said before. Zeolite, after that, special silicates, shifty silicates, co-builders. After that, zeolite P and zeolite X. That is only difference in crystal structure. It is the main thing, but the crystal structure to be a better absorption. What is the properties in detergents? Minimize fiber damage via spectacle particle morphology, minimize incrustation, high water softening capacity, robust performance, inhibition of graying, that is the most important thing, inhibition of dye transfer, because if you graying is when you have a good detergent and he lift everything what is dirt, and after that put on the white. Nobody, you did not nothing. You must inhibit the graying, inhibit the dye transfers, and of course in production and storage, high stability during processing and effective flow. You know, there are three types of synthetic zeolites now modern used in detergents. This is the standard A, standard A, older. After that, P, and after that, zeolite X. Zeolite X, number 3, is now in detergents. It is totally environmentally good. There is no any restrictions for zeolites, and this is what is used for absorbing catalyst, and you will see after. This is how it works. You have a sodium salt, and in the calcium water you exchange. Calcium is going inside, sodium are going outside, so the water is softener. Zeolite as catalysts. What is with this text? I don't know. There are 40 natural occurring zeolites. Most mined forms are, but you remember, this is naturally occurring zeolites. That is not synthetic. Synthetic is something good. The structure can be the same, but synthetically is making in the fabrics, and over these are for mining. So in capital moderate, dozens more artificial, about 150 synthetic zeolites have been designed, and so on and so on. And now I will show you the most good and the most preferred use of zeolite is as catalyst. We have X, Y, and EEM5 zeolites. There are a lot of catalyst reactions, just a few examples. Here is a microsized zeolite epsilon, from N-heptane, catalytic cracking, light olefins. From light olefins, you can go to synthetic gasoline. That is something that is very much in in use that is, some people say that even Germans in Second World War have something like that, because you know that Hitler was not have no source of oil, but as you know, his tanks was all around Europe. Something said that it was a gasoline of coal, and something said it is some catalytic cracking on air happened to light olefins, because light olefins can be used in a robust motors like gasoline, in a robust motor, not in this very fine, but in a robust motor can be used. FCC catalyst, we did it with Birach in first year of this century. This is zeolite epsilon, zeolite epsilon. From zeolite epsilon is example that he makes in Kikinda from natural gas. He makes methanol with zeolite epsilon. Zeolite epsilon is a catalyst they can make from natural gas a lot of products. One of the product is methanol, and after that acids, organic acids. So you see, from FCC, the main purpose is from long chain alkanes. So it is something that is from the oil, but it can be from the oil. It removes from oil. We can have a branched alkynes, small alkynes, branched alkynes, or even aromatics. A lot of money are inside in this FCC catalysis, with high ratio. There is about, I don't know, 20 or 25. This zero tips. So a lot of money is this too, because with this long chain alkanes, you can use things that are waste from oil to make some good things. In the last 2 years, 5 years, absorption of CO2 and around 0.5. It is main things, because there is a, you know, that CO2 is guilty for everything now, guilty for everything, for these climate changes, for everything is CO2 guilty, with sugar and fast food. There are three things: fast food, sugar, and CO2. So CO2 can be absorbed on zeolite 5A, and the N2 can be absorbed on zeolite 5A. This part we used absorption of some part of N2 on zeolite in thermal plants. Why? Because you know that thermal plants cannot make ideal like nuclear plants, so they use coal. Because coal is not ideal, they put air to have a good burning of coal. But air have 78% of nitrogen. We did experiment with zeolite 3 from 78 to 72, just 6% of nitrogen to be used in zeolite. The results are more than good. Better flame, almost all is going in burning. Much better results in thermoelectric plant, only with 6% smalling of nitrogen in the air that are going in the flame. So that will be a great thing to make it. Also with this CO2, but I must say, you as a director of institute, this CO2 story is only to have money from Europe. To have money, they give money. If you said I can make a absorption of CO2, they give money at this afternoon, in the afternoon. If you can make money, that will be a very good. Absorption of we studied a lot of how it's working, and we studied here by neutron emission what is the mechanism of absorption of CO or zeolite on surface surfaces. You see there is a 3.3 angstroms. So we was trying to explain to each other: is it only a physical absorption or is it something chemical? Because if it is physical absorption, you will make it. But when some other gases come, they will go away. But if it is chemical absorption, they will stay. So as far as we understand, there is a good chemical absorption. So this is a quite good way to take money from European countries, from European funds. So how it's going for 5A zeolite. Of course, we have this study here. we recognize the place where it's going, CO2, and every other components. This is absorption isotherms. I don't have to everybody who know physical chemistry, absorption isotherms of CO2 and zeolite at different temperatures. Different temperatures, very good. Kilopascals, absorptions, more even 4. Now, in the last few months, there is a lot of discussions about zeolite 13X. It is very good modern zeolite. And they said the main thing in zeolite 13X is nature. Why? Zeolite 13X was prepared from bentonite. When you say to everybody, bentonite is a rock, it can be mined. Bentonite. So if you make a zeolite 13 from bentonite, it is not too complicated. You use nature. They say, well, it's natural product. It is not like synthetic zeolites. Everybody wants to be natural products, give money for that. And the raw material is here at the thermal. So we make that zeolite, and of course, X-ray powered and so on. So bed surface was about 700, high microporous volume, exhibit high CO2 capture, 211 milligrams per gram, and very good selectivity to NO2. It is very good. It is very important because you know that in the air there is a 78% of NO2, and CO2 is 500 ppm, so something like that. In the gases of good factories, there is about 20% of CO2. So this is 37. Selectivity is 37, 25, and 1 bar. So no lot of money for the pressure for nothing. This we think that this 013 will be in the next few years very good, more than good for absorption of CO2 because of this. We can prepare it from bentonite, and always when you use natural sources, you have advantage than you use only chemical sources. And of course, after that high chemistry, the main problem in the 21st century is food, and a lot of people, a lot of food. We have a guest from Vietnam, and I said to them, how many of you are? They said 90 million. I said, what? 90 million. 90 million only in Vietnam. We even don't recognize that Vietnam is a big country. For example, 90 million. Indonesia is 230 million. So the food will be the great problem in the next 2 years. And ion exchange zeolite properties of zeolites can be used in agriculture because of their porosity and high ion exchange capacity. They can be used for raw carriers of nutrients and the medium for new nutrients. And what zeolites are used for in agriculture, even natural zeolites and synthetic zeolites. Organic manure, odor management, that is very modern in Europe. When you make a mixture of zeolites with organic manure, there is no smell. No smell. Nobody don't believe, but it works. No smell on the farms. And it is very important because, you know, in Switzerland, in all the countries, you can be on job because some farms are smelling to other. Nitrogen management, phosphorus management, slow release of nutrients, very important. Very important because, as you see, the climate is changed everywhere. Rains are like never before. There is no rain, and after that, in one day, it falls 100 liters of rain. So everything is going to zero after 100 of liters. So this slow release of nutrients is of the main importance, having in mind new processes in Europe, new climate processes in Europe. And that means a lot of rains in 1 or 2 days. Because if you don't have a slow release, everybody will go to zero. Every time you put the money out. Slow release of herbicides, improving soil properties, remediation of contaminated soil, and wastewater treatment. Animal feed additive, of course, animal feed is more than business in our world. Alpha toxin sequestering effects, alpha toxin such as you remember that problems with alpha toxin, elimination of mycotoxin growth, ammonia binding effect, elimination of ammonia toxic effect produced by microbial activity, pancreatic enzymic activity, improved facial and visual precursor, reduction of the social toxic products in intestinal metabolic degradation, such as precursor, retarding ethanol digestia, and slowing passenger digestion to the nutrients and more efficient release of nutrients. But this is one of example. Ordinary quinolpterolate. Ordinary. We have in Serbia in three places in Serbia. 3 places. Vranje, Koponik, and 2 places in Koponik. Ordinary quinolpterolate, 72 days. Maize is one of the culture that is in Serbia. No, you know that. Kukuruz, što bi se rekao. This is when you use where this is standard. This with quinolpterolate. Look the difference. Look the difference. Double. Total. Just think about that. Ordinary quinolpterolate. Ordinary. We can make it with synthetic zeolite even more. But it is not expensive, nothing. Just remember that. And pH, nothing special. We don't make any change in pH. Just total nitrogen, exchangeable kalium. You know that in agriculture it's very important kalium to be exchangeable to go to the plant. Very, very, very good thing, and we are thinking that we can make some business with our friends from Vojvodina to make a good job with that. And this is this is in the picture. This is all this in the picture. This is rain before and after rain. When you have a lot of rain, everything is going up. When you have zeolite, everything is here. So think about that. Think about this, because you are science. Of course, if you want money, this. If you want money, this. But from this, from bentonite to 0.26, European will be, when you have this, Europe money will go to you. Because then there is no problem. And of course, if you have a good back, then this. Then this, where is this? No. Just to see. For the thing that changing in the coil, in the thermal plant. Absorption of this. Thermal plant. Absorption of NO2. The coil is going much more. For somebody who doesn't know, my country Serbia that I very much like, but have as we see about 6 million people, have to annually use 40 million tons of coil, 40 million tons to go to 4 thermal grades. And for example, nuclear energy for whole Serbia will be about 1 ton of this uranium if we have a nuclear electricity. So think about it. If you have a good potential, good chances to go to electropower company, think about it for European money. This, and of course, agriculture. It's something that we have on 3 places. Think about it. If you have any questions, please let me know.
Thank you very much, Dr. Blagojevic, for introducing your institute and for letting us know how zeolites can be applied in industry. We have time for just one quick question, really quick question.
Ako jedno, onda neću. Ako jedno, onda.
Yes, please.
$62 years. I'm 30 years in Institute is 62. No optimistic. Lenin price.
For me, this was very optimistic presentation because of application of science in real industrial way. We are working with production of cement based on waste material, and I don't have experience with zeolites. And I have a question after this absorption of CO2. what kind of product is left? Is this waste material or could be reused?
No, the main thing is to absorb CO2, and after that, in one pressure swing process, you CO2 put to make gasoline, to make synthetic gasoline.
Okay.
Yes,
that
to
was
make
the question.
you put that zeolite with CO2, and then you have a pressure swing. Put pressure, zeolite is going on that synthesion of light olefins. That is benzene. That is gasoline. Synthetic gasoline.
Then you don't have a waste after.
No, synthetic gasoline can be used not in the modern car.
Mhm.
Who talks that talks bullish. Not in, but synthetic gasoline can be used in because there is no sulfur in synthetic gasoline. Synthetic gasoline can be used in all thermal processes because it is very pure. It is more pure than diesel. It is more pure than mazout. More because there is no sulfur. Sulfur is the main problem from oils that have sulfur, and synthetic gasoline have no sulfur because there is no.
And considering the application in permanence in food, I suppose that radon emanation is lower in synthetic zeolites than in the natural, no?
In synthetic, we can, yes, in synthetic, we can make everything you want. It is only when BASF was with us, they said we can make 50 polymers, but in German, what's costed us? How much that's cost? Yes, in synthetic zeolites have zero radioactivity, of course. As far as I know, and I know in Vranska Banja, that natural zeolite, it is Nemetal Vranska Banja, it's a company, no radiation, it is less than natural radiation. I know that because they sell their products to the best hotels in France, and they use it in the refrigerators to absorption of smell. For example, if you have a all foods in refrigerator and in good French hotel, they put zeolite from the Vranska Banja, and there is no smell changing. Very interesting, yes. But nobody. Problem of this of all countries in transition is that they put on television singers that are talking about COVID, about vaccines, politicians and everything. Nobody are thinking about what we can do. Just what we can do. Just not we, all Europe, or all Balkan, I would say, Balkan, what we can do. We are talking about, is it good to be vaccinated or not? And about that are talking singers and dancers and something like that. And we are not talking about this. This we have. No Germany, no Bicep. This we have. We have this. Try on 1 hectare, 200 hectares. Try. Maybe we make some mistake. Maybe 600, but not 654. But it's never. Obvious difference. Try this. Try what we have. And that is the problem. That is the problem because this modern science goes to some up science, to plasma, to lasers, to I don't know what. And this level is uncovered. This level is uncovered.
This was the reason why I said optimistic presentation.
Yes.
Thank you very much.
Thank you very
Professor
much.
Topic.
Just quick, please, Professor
Yes.
Stefanic.
Our product was used for Heidelberg cement in Germany,
Yes.
but this presentation is with better results because Stevan used this zeolite under 1 bar atmospheric pressure absorption. This is excellent.
Yes.
And my question is for comparison between our results in autoclave under high pressure.
Yes.
How many is this absorption rate? How many kilo of CO2 per ton of zeolite?
Far as we calculated,
Our results is 350 kilo CO2 per 1 ton of slag.
yes, we have 200 milligrams per gram.
Okay. This is
Yes.
between slag and olivine in our case.
Yes,
but
this is.
your
But the main
cost-
thing is this:
Yeah.
you can give everything,
Yeah.
but if this is not good, nitrogen will put it away.
Okay.
That is the main thing. If it is not good, if it is 1-to-1, no. nothing because there is lots of nitrogen. Yes. Yes. We know crystal structure. We know 013x. It is X type. Yeah, yes. Yes, 13x. Yes.
Great. This is really interesting topic. We can continue. Yes, but
Maybe-
we have a next plenary speaker. So please, we will have a coffee break for 10 minutes and then we are returning back for the next session. Thank you very much. Nisam stigao vremena. Vidio sam da ima nešto filmova. Nekog ekstra. Da otvaram pa sam... Pa ne, ja bih prvo uzeo sam.
Ladies and gentlemen, we now continue with the second session for today. I now invite the presidency to take their seats today for the second session. The moderators are Professor Đenđi Vaštar, the Faculty of Sciences, Novi Sad, Professor Ljubica Vasiljević, Faculty of Technology, Zvornik, and Professor Srećko Stopić, Technical University of Aachen, Germany. Let's give a warm welcome to our presidency.
Ladies and gentlemen, we have to continue with our program. Today, I have good opportunity to be with my friends and colleague Genji and Ljubica. We will continue with zeolite and this topic regarding catalyzed. And we have associate professor from Czech Republic. And this is Maria Shamshi, Faculty of Science, Department of Physical and Macromolecular Chemistry, Prague. And please to give us your lecture. And
before Maria starts, Maria Shimsi received her master's degree in chemistry from the Lomonosov Moscow State University, Russia. Then she joined the LV Pisarjevsky Institute of Physical Chemistry, the National Academy of Sciences of Ukraine, where she completed her PhD in 2013. She spent 1 year as a postdoctoral fellow at J. Hayrovsky Institute of Physical Chemistry under the supervision of Professor Cheika. From 2014 to 2016, she continued her research work at J. Hayrovsky Institute, being supported by the Grant Agency of the Czech Republic. Maria holds a position of assistant professor at Faculty of Science, Charles University from 2017. Her research interests are focused on the design of zeolite catalysts and FTIR study of nanostructural materials. And some highlights of her research are tailoring the active sites in zeolite-based catalysts and characterization of nanostructured materials using FTIR spectroscopy. So, Maria, let's greet Maria with a warm applause.
Thank you very much for the kind introduction. Good afternoon, dear ladies and gentlemen. First of all, I would like to thank the organizers for this great event and for inviting me here. And as it was said, I am a material scientist and my research is mainly focused on zeolite catalysts. My goal is to design the efficient materials for the environmentally friendly production of important chemicals, and it is my great pleasure to share some recent achievements in this field today with you. As you already know from the previous presentation, zeolites play a key role in different industrial processes. For example, in oil refinery, they catalyze different reactions to transform crude oil into high quality fuels and petrochemicals. In water purification and waste management, zeolites act as adsorbents and ion exchangers, where they removed harmful compounds from air, water, and soil. Last but not least, we use zeolites as the components of washing powders, where they act as water softeners. For example, zeolite A is used as a component of well-known Ariel, and zeolite P is a component of Persil. So it follows that all we use zeolites on a regular basis in our everyday life. Such various fields of applications stem from useful properties of the material. So let's have a closer look on zeolites' characteristics. Basically, zeolites are crystalline microporous aluminosilicates, and the basic element of their framework is tetrahedron, where the central T atom is either silicon or aluminum, and it is connected through the covalent bonds to 4 oxygen atoms. These tetrahedra are connected through shared corners and form more complex secondary building units, which finally make up the resultant framework. Obviously, pure silica frameworks are electroneutral. They don't contain any active sites and they cannot be used as catalyst or ion exchangers. But if we place aluminum into the framework, it becomes negatively charged. And if this charge is compensated by a proton, zeolite acquires Bronsted acidity. In turn, coordinatively unsaturated aluminum atoms act as Lewis acid sites. Due to the presence of such acid centers, zeolites act as solid acid catalysts of relevant industrial reactions, such as cracking, isomerization, Friedel-Crafts acylation, alkylation, and others. Zeolites are unique catalysts because they withstand the conditions which usually challenge many other materials. For example, high temperatures don't bother zeolites. The temperature up to 600 degrees is okay. And due to this extremely high thermal stability, we can separate zeolites from the reaction mixture and regenerate the catalyst at elevated temperature. But the most interesting thing about zeolite catalysts is their uniform microporosity. The size of micropores in zeolites is of the same range like small organic molecules. And due to this, zeolites can discriminate molecules based on their size and shape. In this video, you can see how zeolite pore accommodate a molecule to be transformed. The countless number of such pores in tiny amount of a catalyst act like millions of test tubes where chemical reaction takes place on the active sites. And because each zeolites feature specific size and shape of the pores, it can selectively act on the targeted molecules and show shape selectivity. For example, reactant shape selectivity exclude from the catalytic cycle the reactants which sizes exceeds the size of micropores. Product shape selectivity prevent too bulky molecules from escaping zeolite pores, and transition state shape selectivity prevents the formation of too bulky intermediates. There exist natural zeolites and synthetic zeolites. The only framework building elements in natural zeolites are silicon and aluminum, and synthetic materials are much more chemically diverse. By mimicking the conditions of zeolite formation in nature, we could incorporate different elements into silica frameworks. So they are boron, gallium, iron, titanium, tin, and even rarely abundant germanium. In this way, we could generate different acid sites. The elements with typical oxidation state +3 mostly generate Bronsted acid centers, and those covalent elements which are undercoordinated in zeolite framework contribute to Lewis acidity. Natural zeolites were formed due to the deposition of volcanic ash in ancient alkaline springs and under hydrothermal conditions. And this process took millions of years in the nature. Fortunately, in chemical laboratory, we can achieve the same or even better result in several days. For that, we simply mix different sources of framework building elements and apply high temperature and pressure to initiate the nucleation and crystal growth processes. A good thing about the synthesis of zeolite in the laboratory is that we can design the properties of final material by affecting the kinetic and thermodynamics of different steps of crystallization. For example, for the compensating of the negative charge of the framework, we can use not only naturally abundant alkaline and alkaline earth metal cations, but also organic compounds such as quaternary ammonium and phosphonium salts. In addition, we can use so-called inorganic structure directing agents, such as germanium, which facilitate the formation of previously unknown zeolites containing cubic units where germanium is mostly located. Some of those frameworks are prospective for shape-selective transformation of bulky molecules because they contain extra large pores with sizes close or even exceeding 1 nanometer. One of the examples of such zeolites is extra large pore UTL framework prepared in the presence of germanium. As you can see, in comparison to commercial MFI and beta zeolites, this framework contains much larger micropores. On the other hand, the chosen commercial zeolite has higher concentration of acid sites. To assess if extra large porosity provides any advantages for the catalysis, we tested this set of materials in acid catalyzed reactions involving molecules of different sizes. The first reaction was disproportionation of toluene into benzene and xylenes. As you can see, in this case, extra large pores do not provide any benefits because commercial zeolites achieved the same or even higher conversion values. In alkylation of toluene with isopropanol, which involves slightly larger molecules, extra large pore UTL behave better than a commercial MFI zeolite, but still it did not overcome commercial zeolite beta. The last but not least reaction under our study was the benzoylation of paraxylene, which produces white bulky dimethyl benzophenone product. In this case, strong adsorption of this product on the acid sites of commercial zeolites rapidly deactivate those catalysts. But this effect was less pronounced for extra large pores. Thus, aluminum substituted UTL zeolites showed the higher activity. Next, we decided to check how the nature of acid sites influence the performance of a catalyst in this acylation reaction. For that, we incorporated different 3-valent elements into the framework. All the catalysts showed the same concentration of acid sites, but different fraction of strong acid centers showed here with red dots. Thus, the average strength of acid centers increased from boron to gallium and aluminum. Weak boron acid centers were inactive in this reaction. Aluminum acid sites were active, but after some time, they deactivated due to the adsorption of this product. The highest activity was achieved over gallium substituted zeolite with medium acid strengths, because such sites sufficiently activate the reacting molecules and also provide an easy desorption of the product. Thus, a combination of isomorphous substitution and structure directing propensity of organic and inorganic cations allows us to adjust the properties of zeolite catalysts for specific applications. But besides extra large pore zeolites, the materials with enhanced accessibility of acid sites can be prepared by the synthesis of zeolites in the form of nanocrystals and nanolayers. Such materials show high external surface area covered with easily accessible acid sites, Those sites are mostly formed by coordinatively unsaturated aluminum atoms and shows Lewis acid character. So for the synthesis of nanocrystalline zeolites, we can affect different steps of crystallization process. In this example, we vary the composition of reaction mixture, temperature, time of the aging and crystallization steps. In this way, we could decrease the rate of crystal growth with respect to the rate of nucleation. And using this approach, the most of industrially relevant zeolite catalysts were synthesized in the nano-sized form. In our study, we systematically varied the dilution of the reaction mixture in the synthesis of zeolite beta. In this way, we could produce nanocrystalline zeolites with different sizes of the crystals and different external surface area. Those catalysts were studied in the one-pot cascade Prince-Friedel-Crafts reaction, which allows to synthesize tetrahydropiran containing valuable compounds from three-component mixture containing aldehyde, aromatics, and allylic alcohol. The yield of targeted product correlated with the external surface area, and the highest activity was achieved for the catalyst synthesized under optimal conditions. This yield competes with previously reported result for the homogeneous system, so it can be considered as a remarkable step forward towards environmentally friendly production of such compounds with the aid of solid acid catalysts. Turning back to the synthesis, another approach to create zeolite nanocrystals consists in using specially designed silylating agents, which anchor on the surface of growing nucleus and prevent the crystal growth. We found that the changing in the ratio between the concentration of those modifiers and inorganic components allows to tune the crystal sizes and also textural properties of synthesized materials. At the same time, we affect the fraction of surface Lewis acid sites. So by using this approach, we optimized the properties of zeolite nanocrystalline catalysts for the cracking of polyolefins. With increasing the concentration of organic modifiers, we could improve the external surface area of our catalyst, but at the same time, we decreased the Bronsted to Lewis acid sites ratio. In the optimal catalyst, we could achieve the balance between the accessibility of acid sites and Bronsted acidity. We can not only decrease the crystal growth of zeolites in all three directions, but by using special organic structure directing agents, we can produce zeolite nanolayers. In such type of organic molecules, the nitrogen containing part is responsible for the formation of zeolite, and this long alkyl chain prevents the crystal growth. In our research, we designed such type of organic molecule with variable lengths of nitrogen containing part and use these molecules for the synthesis of 2D MFI zeolites. These materials had the same chemical composition and acidity, but different thickness of the nanolayers, 27 angstroms, 21 angstroms, 17 angstroms. In comparison to commercial zeolites, our designed catalysts showed much higher total surface area and external surface area. And both these parameters correlated with the thickness of zeolite nanolayers. Next, we showed that produced 2D zeolite catalysts are efficient for the synthesis of heterocyclic compounds by annulation of phenols with different sizes. In this part of the slide, I visualized the sizes of reacting molecules, in this case, phenol and methylbutanol, and the sizes of pores in zeolites. From this picture, we can assume that all external and internal acid sites would be accessible for reacting molecules, but the diffusion limitations may increase from MFI to beta and USY and be the lowest for our 2D zeolites. More specifically, the yield of targeted product, shown here with red bars, correlated with the total surface area in our catalyst. But the benefits of 2D zeolites became even more pronounced when we used bulkier 1-naphthol substrate. In this case, we can assume the restricted accessibility of acid sites located in micropores of our materials. And indeed, the yield of targeted product correlated only with the external surface area. As 2D materials had much higher values of external area, they perform the best in this reaction. Thus, the recent advances in zeolite synthesis allowed us to produce several types of materials prospective for the transformation of bulky molecules. They are extra large pore zeolites with exceptional intracrystalline porosity, also nanocrystalline zeolites with enhanced external surface area. And all this was achieved using assembly of simple species into final complex framework. Alternative approach for the synthesis of new zeolite catalyst is based on the transformation of already formed zeolite frameworks into new materials. For that, we need to have a proper starting materials, and they are germanosilicates, featuring regioselective location of germanium atoms in small cubic units, and also hydrolytic instability of germanium oxygen bonds. In our research, we studied the frameworks composed of dense silica layers connected by germanium enriched cubic units. And we found that the treatment of such zeolites in water or acid selectively remove those cubic units and disassemble the framework into crystalline layers. In the next organization step, we applied special conditions to arrange those layers in a specific manner. And finally, we reassemble or condense the layer into new zeolite structure. The only difference between the parent and daughter zeolite is the structure of the interlayer connections, because the layers themselves remain intact under applied conditions. So this new synthetic method was called ADOR based on its main steps, which are assembly, disassembly, organization, and reassembly. And if we compared this top-down synthesis with conventional synthesis protocol, the outcome of which is usually hard to predict, the ADOR allows us to rationally synthesize new zeolite structures with predictable frameworks closely resembling the parent zeolite. UTL was the first zeolite successfully subjected to this ADOR transformation. As a result, after disassembly step, we got new layered IPC1P material, and after reassembly, IPC4 zeolite. The interlayer distance in those daughter materials is lower in comparison to UTL, and the reason is that we replaced quite large interlayer double four-ring units with oxygen bridges. By varying the conditions of the disassembly step, we could produce other UTL-derived daughter zeolites with the same structure of the layers, but different interlayer connectivities. In this way, we discovered IPC7 zeolite with alternating double four-ring and single four-ring units, IPC2 zeolite with single four-ring units only, IPC6 with alternating single four-rings and oxygen bridges, and IPC4, which we already discussed. TEM images evidenced different structure of the interlayer connections in the new materials. And due to these different connections, we could systematically vary the micropore sizes, which increased from IPC4 to IPC6 and 2, and finally reached the maximal value for extra large pore UTL zeolite. Next, we showed that the produced set of materials are excellent model catalysts to study pore size activity relationships, both in Brønsted and Lewis acid catalyzed reactions. For that, we designed a set of catalysts containing either aluminum sites or titanium sites and studied them in two model reactions. For aluminum-containing zeolites, we used tetrahydropyranylation of alcohols of different sizes, such as ethanol, 1-hexanol, and 1-decanol. And titanium-substituted zeolites were studied in epoxidation of 1-hexene and cyclohexene. In general, for the smallest substrates, the conversion maintained independently on the size of the pores in zeolites. But for the bulkiest substrates, it gradually decreased with the micropore sizes. Our findings match the predictive kinetic analysis and confirmed that this model catalyst can be used for other reaction to assess the effect of acid sites location in different micropores. At this point, we start thinking about recovery and recycling of rarely abundant germanium to decrease the cost of our catalyst. And finally, we came up with the method which allows to recover more than 90% of germanium. It has several steps. First, germanosilicate is treated with water to dissolve germanium. The hydrolyzed zeolite is isolated and used for the preparation of catalytic materials, while germanium is recovered in the form of germanium oxide after evaporation of the water. When we reuse this recovered germanium for the synthesis of new germanium-containing materials, we found that we can adjust the selectivity of zeolite crystallization or the structure of formed product based on the separation method of germanium from the parent zeolite. If we used normal filtration, parent zeolite microcrystals still were present in the mixture with germanium oxide. And those microcrystals act as seeds, which facilitate the formation of parent zeolite independently on the synthesis conditions. On the other hand, if we carefully remove those zeolite seeds by, for example, microfiltration, we can get a versatile source of germanium for the preparation of different zeolite structures. At this point, I would like to switch the topic from zeolites to metal catalysts, because they also play an important role in the redox reaction for the synthesis of fine chemicals and neutralization of volatile organic compounds. The regular metal zeolites usually suffer from aggregative instability and poisoning from the component of reaction mixture, and zeolites can help to solve this issue by encapsulating of metal particles in their voids. If such zeolite supported metal catalyst is properly designed, the metal particle appears to be protective from poisoning component and from aggregation with neighboring metal particles. On the other hand, zeolite support may provide shape selectivity for such catalytic system. For the preparation of zeolite supported metal catalyst, there was reported several methods. The first one is co-crystallization strategy, in which the encapsulation of metal nanoparticle is intended to occur simultaneously with the crystallization of a zeolite. The problem here is the very fast precipitation of metal precursor under harsh conditions of zeolite crystallization, and the necessity to develop quite sophisticated protective agents to balance these rates of metal precipitation and zeolite crystallization. Another methods are based on the soaking of preformed zeolites with metal precursor, either by ion exchange or impregnation. These methods are easy to realize, but they are limited by the metal precursors, which sizes do not exceed the pore size of zeolites. More to that, the loading of metal is restricted by ion exchange capacity of a zeolite. On the moment, the most efficient approach for the preparation of zeolite-supported metal catalysts is based on the encapsulation of metal precursor into two-dimensional zeolite, followed by condensation of the layers. In this method, the metal precursor is introduced during the swelling of layered material with surfactant molecules. In our study, we found that the changing in the size of alkyl chain in this surfactant allows to regulate the interlayer distance in a zeolite, and as a result, the sizes of formed metal nanoparticles. For example, when we use C18 surfactant, the resultant nanoparticles of platinum had an average size of 20 angstroms. However, when we decrease the size of alkene chain to 12 carbon atoms, we could stabilize the nanoparticles with sizes smaller than 9 angstroms. We used the prepared catalysts for the hydrogenation of nitro aromatics and found that in comparison with commercial palladium catalysts supported on carbon, which transform the substrates of different sizes, our catalysts showed shape selective properties because only molecules which fit the pore sizes of zeolites were reduced. This is a result of quite good dispersion of metal nanoparticles in a zeolite confirmed by TEM Also, we found that our catalyst can withstand at least 5 catalytic cycles without changing the dispersion of metal component. At this point, I would like to stress that designing of a new zeolite catalyst is important, but practically impossible without understanding surface chemistry of the prepared materials. And for this purpose, IR spectroscopy is a powerful and very helpful tool, which we use in my group. For qualitative and quantitative analysis of the surface functionality, we constructed this in situ setup for the experiments under high vacuum. And more to that, we have the setup for operando experiments to study catalyst under working conditions and address different steps in reaction mechanism. Here I have shown the examples on how we assess the different behavior of 2 catalysts in transformation of this biomass-derived furfural. We found that the first catalyst selectively produced the molecule shown here in blue, and this catalyst yielded selectively the red product. To understand the origin of this difference, we performed IR study focusing on the interaction of catalyst surface with this blue compound, considered intermediate on the way to the red product. Upon heating, the molecules of blue intermediate rapidly leave the surface of this catalyst, which indicated a weak interaction between intermediate and catalysts, which might be responsible for the termination of the catalytic reaction as soon as the blue product is formed. On the other hand, special functionality of this catalyst allowed strong interaction of its surface with blue compound and its transformation into the red product. This brings me to the conclusions. I hope I could show you that the design of zeolite catalysts is important for the intensification of many catalytic transformations. Hydrothermal synthesis is the most developed method to tune the important characteristics such as crystal size, chemical composition, micropore size of zeolite catalyst. But it has a limitation with respect to the structure of formed material. The predictability of the formation is low. In contrast, recently developed ADOR synthesis approach based on the rich chemistry of germanosilicate zeolites allowed rational, intelligent synthesis of zeolite catalysts with predictable structures and adjustable chemical compositions. Still, there is room for further discoveries, for example, the extension of ADOR approach to germanosilicates containing not only silica layers connected by cubic units, but also silica wires and silica dots, and also regulation the local properties of acid sites in zeolites. Also, a lot can be done for understanding synthesis, property performance relationships in zeolite supported metal catalysts using, for example, in situ and operando spectroscopic techniques. And this is exactly what I will study within a 5-year project supported by the Ministry of Education, Youth and Sports of the Czech Republic. And for the successful implementation of this project, young people which are interested in nanomaterials and in performing their research at Charles University are welcome to join our group as postdoctoral researchers. For more details, please contact me. And with that, I thank you all for your kind attention, and I will be happy to answer your questions.
Maria, thank you very much for excellent presentation, excellent slide, excellent literature, excellent animation, very professional. I have to say, firstly, I will contact you. Postdoc position is open. And
I can only say excellent present. I hope I did my best. Excellent presentation for excellent Congress.
For me, was excellent that you connected many topics, synthesis, recycling, and this is something what I didn't see at this conference. This is excellent. But do you have some question for Maria? Jelica Novaković.
So first of all, scaling up. This is what we are currently working on in the lab scale, and also we collaborating with the companies to transfer this to the pilot plant scale. And for the wasting, heterogeneous catalysts have benefits with respect to homogeneous ones, because they do not create waste. They, for example, zeolite catalysts, if they are deactivated, we can separate them from reaction mixture. We can calcine them to remove all poisons and adsorbed species and reuse it again.
If I can add regarding upscaling, you've worked in autoclave.
Yes.
Because synthesis 175 degree, about 565 to 6 bar or something. And
what we can do in our group, in our lab, when we are looking for the optimal conditions, of course, we use small autoclaves.
1 liter.
No, not 1 liter, 90 milliliters.
Oh, excellent.
Or even 10 milliliters. But when we are sure about synthesis conditions, we use larger autoclaves, 1 liter, 5 liters. And what is more is cooperation with industrial partners.
Okay, I can say we worked experiment in 10 liter and 100 and 1,000 liter autoclave. Maybe we can connect. I survived it. And,
okay.
And thank you very much. Now, if not question, we have 2 excellent candidates for silica gel synthesis and silica gel application. Excellent company, Zeochem, and Dr. Anna Stojanović, Belgrade University, now in Switzerland, will start with synthesis of silica gel.
Anna Stojanović comes originally from Belgrade, Serbia, where she finished undergraduate studies at the Faculty of Physical Chemistry. She graduated at University of Zurich, where the topic of her PhD was development and applications testing of super hydrophobic silica silane coatings. During her PhD time, she published several highly cited scientific publications and 2 book chapters. After PhD, she did postdoc at EMPA Swiss Material Testing Institute, where she worked on upscaling processing technology of silica aerogels. In collaboration with industrial partners, she has built a pilot plant for silica aerogel production. Besides upscaling, she has also worked on end-user product development and application testing using silica gel product as thermal insulators of building cars and windows. Anna Stojanović started working in Zeochem AG 3 years ago in research and development department in Switzerland. Her current work consists of developing new products based on silica gel for chromatography and securing the top quality of current product portfolio. Let's give a warm welcome to Anna Stojanovic.
Good afternoon, and thank you, Vesna, for your kind introduction. Yeah, so topic of my talk today is silica gel synthesis, and on contrary to most of other talks given today, I will not focus on my current scientific research, but I will try to give the overview of versatility of silica gel synthesis and their most prominent application. And the reason I choose to talk about that today is because Zeoheim used to produce silica gel for 50 years in Zurich, just at the lake. They had a huge factory. And 6 years ago, they decided to outsource their production to alumina in Zvornik. And now silica gel is actually produced in alumina in Zvornik, and it's post-processed at Zeoheim DAO in Zvornik. So I thought since these technologies, so to say, in-house in the Republika Srpska, it would be nice that we have an overview for where you can use it and maybe use it more in different industrial fields. So first, what is silica gel? Silica gel is a amorphous and porous form of silicon dioxide consisting of irregular three-dimensional framework alternating silicon and oxygen atom with nanometer scale voids and pores. As it is by chemical composition, just silicon dioxide, it is eco-friendly, reusable, and recyclable. And it can exist in the three forms. This is like irregular silica gel, spherical silica gel, and monoliths. Visually, its visual appearance is like white to transluminescent, and if we have a monoliths, it is very often called a frozen smoke. So here I just wanted to list some of the most prominent applications of silica gels. Definitely one of the most prominent is as a desiccant. So silica aerogel is widely used all over the world for absorbing humidity and different outdoor smells. The nice part is that once it is saturated with the humidity, you can just heat it up and reuse it again. It is also very often implemented in electronics, where we keep very low relative humidity. This effect is known as a humidity buffering. Also, you can find it in cameras, where it is implemented in the lenses to prevent the condensation of the lenses. Another very widespread application is water filtration. When we filter water with silica aerogel, we can absorb different minerals, or we can also do ion exchange. Also, well-known application is the cat litters. It can be used only silica gel, or it's in a mixture with the different clays, such as bentonite, for example. Also, very important is that silica gel is marked by FDA as a safe as a food additive. And in US can be used up to, I think, 5%, while in European Union is upper limit is 2%. And some applications are like, for example, as anti-foaming and absorbers of toxins, and some proteins in wine, beer, and apple juice industry. And also, currently there are kind of, I think, few master theses in technical faculty of Zvornik, where the silica gel products from Zeoheim are tested as a food additives in industry. I think one of the last which I seen was about using silica gel for the colorization of sunflower oil. Also, silica is very widespread in chemistry. This is something that I will maybe mention later, but it will be mostly discussed in the next talk, which will be given by my colleague, Dr. Victoria Kustoris. So how do we make silica gels? So silica gels are made based on sol gel chemistry. Sol gel process is the method for producing solid materials from small molecules. Process involves conversion of monomers into colloidal solution, so-called sol, that acts as the precursor for an integrated network gel. Sol is defined as a colloidal dispersion of particles in the liquid. As here you can see the schematic illustration how the silica gel is made. So first step is like precursor, which is a stable colloidal solution. Then we have a hydrolysis and condensation to form the sol. From sol, we have a further condensation of these particles to form three-dimensional network structure of silica gel in a solution. And after that, we want to make this network strong, mechanically strong, and to make it mechanically strong, we have to perform the aging step. And after aging step, we are doing the drying. Already this first step from precursors to sol is determining the final properties of silica gel, such as pore volume and surface area and size of a primary particles. And that's why I would like in next few slides to a little bit explain this first part. So here you can see that two most common precursors used for silica gel synthesis. It is a sodium silicate or alkoxide precursors such as TiOS and TMOS. In both cases, we can form a gel using single step or a two-step process. So in case of alkoxide precursors, we can first do the hydrolysis by adding the acid and then add the base and initiate the gelation, or we can just add the base and have a gelation immediately and formation of the alcohol. The same thing is with sodium silicate. We can do first acidification and then formation of the gel, or we can do neutralization and direct formation of a hydrogel. So the precursors is nothing but the starting material for the sol gel process. And as I said, one of the most common is the sodium silicate or so-called water glass, and which is soluble in the water. And here you can see the chemistry in case of sodium silicate. So we have just the reaction of sodium silicate with water and some mineral acid, where we form the salicylic acid and salt. And then these salicylic acids are condensing further, forming silicon oxygen bonds. And as a side product, we have water. So end product looks like in this beaker, we have just the gel, which is like wet gel, which is like a silicon dioxide, and pores are filled with water, and that's why it's called the hydrogel. While if we use the second most common precursor, TOS, tetraethyl orthosilicate, first step is hydrolysis of tetraethyl orthosilicate with water, forming salicylic acid and corresponding alcohol. And then in the second step, we have two competing reaction mechanisms, which is water condensation and alcohol condensation, leading again to the same silicon dioxide structure. But in this case, we have pores are filled with the alcohol. So we have a formation of so-called alcohol. Silicon alkoxide precursors are offering a better control of final parameters of silica gel, but they are way more expensive and require the use of expensive organic solvents. So besides this first step, which I said is decisive in primary particle size and pore volume, the second, so to say, most important part is drying of a silica gel. Drying is very important because silica gel is very hydrophilic by nature, and inner pores are filled. If the inner pores are filled with water, we have a very strong capillary forces which are doing the drying, causing the shrinkage and collapse of the gel. So we really have to perform strict drying regimes to be able to minimize the shrinkage during the drying. In case of the alcohol gel, where we have ethanol, capillary forces are a little bit less strong, but still, if we use the ambient pressure drying, the minimum shrinkage which we can achieve is 30% in comparison to the starting volume of the wet gel. So, and then there is also a special form of silica gel called silica aerogel. Silica aerogels are formed when the drying is performed under the supercritical conditions, and we keep the porous structure of gel the same as it is in a wet gel. So how is it done? We start from the alcohol gel. We put it in the autoclave. We exchange it with liquid CO2, and then we dry it under the supercritical condition. Silica aerogel is renovated as the lightest and the lowest density solid material known. It's barely more than the density of the air. Silica aerogel has a porous sponge-like structure in which more than 98% of its volume is the empty space, actually air. And because of these properties, they are super insulators and have a tremendous growth potential, particularly for building retrofit, industrial, and pipe insulation. So why they are super insulator? The explanation is the constant effect, which means that if we have a pore size which encompasses the gas, which is in the same range as a free part of the gas, the thermal conductivity and convection is decreased. So we have a very, very low thermal conductivity. And just to kind of demonstrate that, there is this famous photo. There is this famous photo about silica aerogels, which you can find everywhere in the internet. So here we have a Bunsen burner with 1,200 degrees, and we have just like a 2 centimeters of silica aerogel and flour on the top, which can last for hours, staying fresh. So, of course, since materials have such extremely nice extreme properties, it is already recognized in industry, and it can actually help fighting the global energy consumption, because heating, ventilation, and air conditioning in buildings, including industrial and commercial buildings, account for approximately 40% of the global energy consumption. And the energy consumption of heating, ventilation, and air conditioning system in buildings can be lowered by up to 75% with minimal effort by installing the proper thermal insulation. And of course, by now, a lot of big companies recognize that and came out with the final product on the market based on silica aerogel. One is Aspen aerogel, and the other example, for example, BASF. So here on this image, you can see the aerogel blankets produced by Aspen aerogels, which is used for industrial pipeline insulation. So you have just like a insulation, maybe 2 to 3 centimeter thickness, which is very flexible. And it's also open pore structure, so it's breathable. There is no mold formation, which is way easier to install than in comparison to the standard ones, such as mineral wool, where you would need like 30 centimeters to achieve at least the same efficiency. Another interesting product is, for example, aero brick. So there are already bricks which are filled with aerogels, so you can build your houses from the beginning using thinner walls, which are already thermally insulating and breathable, so you don't have formation of the humidity and the mold. Silica gel in chemistry. Silica gel is used in chromatography as a stationary phase. In chemistry, the pore size which are used in chemistry are between 30 and 4,500 angstrom. For the small pore size silica gel is used in the petrochemical industry, while 35 to 150 degrees angstrom is used in, for example, pharma for vitamin, antibiotics, vaccines, in food and flavor industry, as I said, oils and fats, natural products, in chemical industry for pesticides, lipids, and chemical synthesis, while a very big pore size, 250 to 4,500 angstroms, is mostly used in the biotech industry for vaccines, DNA, enzymes, carriers, biomolecules, etc. As I already mentioned, silica aerogel by its nature is very hydrophilic. So in order to be able to use it in chromatography for all these versatile application, we have to do derivatize. Very often we have to derivatize silica to add the specific functionality. Derivatized silica provides additional selectivity and significantly broadens chromatography application of silica as stationary phase. And hydrophobic silica is form of silica that has hydrophobic groups chemically bonded to the surface. And we already seen these photos today. So these are the hydrophobic and hydrophilic surfaces. And here we can see the contact angle of these surfaces, which is defined by Young equation. And if the contact angle is higher than 90 degrees, we have a hydrophobic surface. Higher than 160, the surface is considered non-wettic or super hydrophobic. While if the surface contact angle is lower than 90, we have a hydrophilic surface. So one of the most commonly used silane for derivatization is octadecyl silane or C18, which makes the silica surface very hydrophobic. And here I just listed the most commonly used functionalities in chromatography, such as octyl, amino, phenyl, cyano, diol, and diol. So everything what I said now was about irregular silica. And there is also another type of silica, which is like spherical silica gel. Spherical silica gel is more mechanically stable than irregularly shaped one, and most commonly is produced by hydrolysis of tetra alkoxysilanes using so-called Stülber process. The reaction produces silica particles with diameters ranging from 50 to 2,000 nanometers, depending on the starting condition. And as a starting material, expensive silicon alkoxide silica precursor is used. Since we are getting smaller particles with very monodispersed particle size distribution, these kind of particles are used for investigating, for example, colloidal phenomena in the biosensor applications, and as well as in liquid chromatography and as a catalyst. Alternatively, spherical silica with bigger diameters can be produced from sodium silicate by employing emulsion polymerization technology. Both processing technologies are way more expensive than irregular silica gel production due to more complex processing and use of organic compounds. And here I just wanted to kind of give you industrial setting of producing silica gel. So in these first two photos, you can see how the bare silica gel is produced using huge reactors, and the whole reaction time for one batch is like 1 week. And then we are getting the hydrophilic silica gel, and from there we can use the step 2 and perform the derivatization and add different functionalities to silica. So this is the last slide actually, where I wanted just to summarize what are the pros and cons of sol gel chemistry and making silica gel by sol gel chemistry. Pros is definitely that we have high purity homogeneous material. We are using very low processing temperatures, which are having a minimal evaporation losses and a low control of a pore volume and a pore size. And the products which we are getting is, as I already said, eco-friendly, is reusable and recyclable. And cons are that we have a high cost of the precursors, especially in case of silicon alkoxide, long process duration, and difficulties in synthesis of monoliths, which I already mentioned. If you really want to keep the monolithic piece, we need to perform the supercritical drying, which is, yeah, energy and intensive and also quite complex. At the end, I would like to acknowledge all these institutions like TEOHEM DO in Zvornik, Faculty of Technology in Zvornik, Alumina DO Zvornik, and my mother company, TEOHEM Ruti, with people from all these four institutions I'm working on the everyday basis for the last couple of years. Special thanks maybe to people who are already here, Dr. Dragana Keshe and Zoran Petkovic. And at the end, I would like to thank you for your attention.
Thank you very much for many information about synthesis of silica and many forms of silica, and of course later we will obtain information about application. And firstly, some question for Dr. Anna Stojanovic.
You mentioned about usage of silica hydrogel as an insulation material, and you mentioned about the thickness 2 centimeter, yeah? And how much insulation it makes?
So thermal conductivity on silica aerogel is like a 17 milliwatts per meter Kelvin, so between 17 and 19. So if you compare, like, for example, with mineral wool, can you hear me good? If you compare it with mineral wool, you would need like a 20 to 25 centimeters. And for silica to achieve the same U value, which is like a measure of how good some material is thermally insulating. And while for silica gel, you would need 5 to 7 centimeters. So 3 times less than mineral wool. That's a kind of ratio.
I'm just wondering, if you look at the insulation materials, the thickness are 7-8 centimeters, and they make like 10 centigrade degree insulation. So what about this silica hydrogels?
Silica aerogels.
Aerogels, sorry.
No.
Yeah.
So yeah, I mean, as I said, I mean, there is you need 3 times less than a standard material to achieve the same value. So if you need 10 centimeters, you said, to reach like minus 10 degrees, then you would need 3 centimeters with silica aerogel. I mean, also advantage of silica aerogel is what they said is like that you have an open pore structure. So you don't have, like in case of other materials, formation of the mold or something.
The other question, which one is more important, thermal conductivity or porosity for insulation?
Both, I would say, because porosity, as I said, helps you living healthy and preventing if it's the right pore size, you will decrease the movement of the gases, so it will actually keep the gas. So I would say the both parameters are important. And what is also important that I would find for application is flexibility.
Thank you very much.
Welcome.
We can discuss more.
Jelica Novaković.
I think this silica aerogel looks like magic material, very smart material, and let's say, okay, it for sure will find application, but yes, it is always about the cost and then about the energy to produce it. So let's hope
Yes.
that we will have an
Yes, and still it is like 3 to 5 times more expensive than a standard materials. That's true. But then it comes into play that you use less of it, and it makes sense to be used on the application where you cannot use, for example, standard material. If you are having like a very expensive like housing and you have a limited space. So then it pays off. Or for example, they already use it in elevators, in hotels where you have also very limited space.
Yes, yes, in smart buildings. Smart
Yeah.
cities, et
So
cetera.
it's all like trade-off, like, but yeah, I hope we will progress further and make it cheaper and cheaper.
Let's hope. Yes, it's really not magic.
Thank you. Thank you for your question.
New question, Professor Genji.
About hydrogen. Have you any information about corrosion property?
I mean, since it's just a silica aerogel, what do you mean, the corrosion if you insulate something with it? Or
Articulation material.
yeah, I mean, this is as I said, this is a very good. Yeah, it is hydrophilic. Yes, yes. I mean, to be honest, I don't know really the results from the long-term studies. I know it is very much used in like insulating the metal pipelines. So I don't see the big problem on a short term, but yeah, long-term studies are still to be done, I guess.
Anna, I have 5 questions maybe after this session. If
Maybe later we can discuss.
if you are not tired, we can give only 2 questions.
Yes, let's do that.
Because in Germany, we worked very much regarding silica gel formation, but in contrast to Zeochem, we work to prevent silica gel formation because our aim was extraction of rare earth elements, and we had to learn about silica gel formation. And you explained us excellent that we need hydrochloric acid, water, and after that silica gel be formed in autoclave. And
I mean, you don't need the autoclave necessarily. You can just do it in ambient conditions.
yeah, this is also possible, and it was not good for us. But the question is, what is the initial concentration of silicium in solution for start of silica gel formation? Did you measure it?
Yeah, anything between 12 and 40%.
Okay, we found about 150 milligram per liter, and
Yeah.
this is first question. Second question, we made also synthesis of nanoside silica, and also we have publication with ultrasonic spray pyrolysis. And the question is how to control particle size. Which parameter is most important, temperature or something like that?
That's a very, I mean, it sounds simple on the paper, but yeah, it's a lot of parameters. And primary particle size, for example, if you're asking the final particle size or primary particle size, what is the question?
The question is how to control for final particle size.
In Stober process, final particle size is controlled by temperature mostly, yes, and the steering speed and these kind of things. But I mean, if you're using, you can also use some more advanced technologies, for example, some kind of membranes or jet cutting, or there are now the different techniques where you can actually force your system to have a certain particle size.
Okay, and next 3 questions are about.
Maybe we continue the discussion later. Yeah.
Later, but that you know about carbonation in autoclave. Okay, now is head of department is Victoria Custodis, originally from Germany, and she worked with Technical University in Aachen, but you will give information.
Dr. Victoria Custodis, originally from Germany, did her master's in chemical and bioengineering at ETH Zurich, Switzerland, with focus on catalysis of renewable resources. At Covestro, former Bayer Technology Services, Germany, and North Rhine-Westphalia Technical University in Aachen, she helped to develop a catalytic system for the copolymerization of carbon dioxide, which is now patented. During her PhD at Van Bokoven's group at ETH Zurich, she investigated biomass conversion for production of renewable-based chemicals using zeolites. With Dr. Patrick Hemberger and at Paul Scherrer Institute, they were able to identify short-lived radical intermediates from the catalytic surface of zeolites using vacuum ultraviolet radiation. In 2017, Victoria joined the research and development team of Zeochem AG Switzerland and supported the development, application, and production of silica-based chromatography gels. She presented Zeochem products at many conferences for peptides, nucleotides, and other small molecules for pharmaceuticals, and also published on preparative chromatographic method development. Since 2019, she has been head of the research and development team in Switzerland and additionally responsible for process optimization and development of deuterated compounds used in chemical analytics, electronics, and pharma. Let's greet Dr. Custodis with a warm welcome.
So yeah, welcome everybody, and thank you for the opportunity to speak here. And I decided from Zeochem point of view to talk about the applications of silica gears. We already saw many varieties of examples, and I will focus on the chromatography because this is a very high value application of silica gels. You need a very high quality product for this. I will quickly go through the principles of chromatography, how it's working, and why silica, as we have the nice introduction from Dr. Ana Stojanovic, silica is a very good material for this chromatographic application. And then I will give you two examples that we actually worked on with our customers at Zeochem on their process optimization. These are real application examples where we will do large scale chromatography. So first, principles of chromatography. Many chemists already know this. You can do this in the lab at the small silica column. You pack your column and you purify your organic compounds, but you can also have it in very large scale. So this is a multi-100 kilogram column packed with silica for a separation of pharmaceutical active ingredients, APIs, or nutraceuticals. Dr. Ana Stojanovic already showed us all those different applications. So I'm building on all this knowledge that you already gained. So principles of chromatography. I always used to say chromatography is a little bit like catalysis, just without the reaction, which makes it much more complicated. Why does it make it more complicated? So you have both chemical forces that decide the retention of your process, and you have physical forces or fluid dynamic forces. So chromatography is molecular affinity-based separation to really purify your compounds. So this is for high-value chemical products. And you have, on the chemical side, you have all these intermolecular forces like van der Waals, ionic, hydrophobic, and hydrogen bonding. And then at the same time, you have those fluid dynamics that you also need to look into. So the good thing is silica is very variable, and you can influence both of these things with silica. So you can influence all the fluid dynamics by particle size distribution, and particle form. We had the granular silica and the spherical silica. And you can also influence the chemistry side of it. So there are many different applications of chromatography, and chromatography is very versatile. So you have it in any different scale, which is here, and also any different purification modes. So in this case, you're basically influencing your chemical purification with the fluid dynamics and the physical process design. So you have here different pressure regimes you are working with. And liquid chromatography is at ambient pressure, flash is like 1 to 10 bars, HPLC is 10 to 100 bars, and UPLC is 100 to open-end bars. And then you need different stationary phases, and you also need, you get higher resolutions if you increase the pressure because of physical effects. But you decrease the scale of your process. So if you work here, you only can inject microliters of your compound, so you purify it. But if you work here in the kilogram scale, you can inject more and you have more process throughput. And then once you have optimized your process scale and your physical process design, you can go and look at the surface. So we have NP is normal phase chromatography, goes up in hydrophobicity of the stationary phase to RP, which is reversed phase chromatography. There we have different intermediate designs depending on what mobile phase you're using. Maybe I should emphasize this here as well. So you can change your molecular affinity on this separation process, not only by designing the surface, but also using a different solvent. So you dissolve your molecule in the mobile phase, that's how we call it. And then it's in this mobile phase, and this mobile phase also influences how well your molecule interacts with the surface area. And this is basically what you also do here. So with normal phase chromatography, you usually use very hydrophobic solvents, and in reversed phase, you use very hydrophilic solvents. And by this, you increase the force of your solved molecule to interact with the surface of your stationary phase. So why is silica so good? Silica has a very high mechanical stability. I mean, my colleague already mentioned this, and it also has a very high chemical stability. In contrast to other chromatographic materials, it doesn't smell, and no matter what solvent you use. You can also have a surface functionalization. This is also very well explained by my colleague, because you have here all these hydroxyl groups, and they can attach other ligands, and then you have very different surface functionalities. And if you really if you are very good in processing silica, you can tune your pore size and your particle size, and you can also tune your pore volume. And the pore size and the pore volume are very important for the application. And another very big advantage of silica is it's very available in bulk. So we can produce tons of it, and you can pack many, many columns with it. And it's not like a biological resin or some polymer beads, which are batch-wise produced in, I don't know, 10, 100 kilogram scales. And they're much more expensive. So I'm coming to my first application example. So this is with SFC. SFC is supercritical fluid chromatography, which sounds very expensive, but it actually isn't compared to other chromatography processes that use organic solvents like ethanol or acetonitrile, also sometimes toxic solvents. Supercritical chromatography is a very good way to separate your product efficiently, because at the supercritical stage of carbon dioxide, the carbon dioxide is a very, very potent solvent to dissolve your molecule. And it has a very, very low viscosity. And there we come back to the fluid dynamic optimization with this low viscosity. You have a lower back pressure of your packed bed. You can run higher flow rates, and then you have faster run times. And that just means you have faster throughput. You're producing more, so everything becomes cheaper. It has a long, strong solubility of your target molecule, and it's actually non-toxic, non-flammable. It has a high installation cost, but once it's running, it's very low cost. We can recycle the carbon dioxide, and you can separate your analyte very quickly from the carbon dioxide because you just evaporate it and you have your analyte, in contrast to other chromatographic processes where you have very energy intensive separation processes like distillation, lyophilization, and all these kind of things. This is very cheap. So it's actually seen as the most ecological of the chromatographic processes. So there was an example, a production facility producing all those omega-3 fatty esters, which are, according to literature, very healthy, and they're helping with heart diseases. So they get crude oil from algae or fish oil, and they want to purify. And to have it as a pharmaceutical product, you need to purify it to 99% plus purity of the chemical compound. And as you can see, all these fatty acid esters are looking very, very similar. They only differ in 1-2 carbon hydrochains and 1-2 double bonds. So how do we separate this? We use SFC with pure carbon dioxide, and we test different surface functionalities. So here we wanted to see how the surface is impacting the whole separation process. And we use this material because it has a very small pore size, average pore size, but a high surface area. And since these molecules are very small, we don't expect any diffusion limitations. And with those different surface functionalizations, so you already know, we have bare silica with selenol groups, which is very, very hydrophilic. And then we have on the other end, the C18, which is very hydrophobic. And the C18 didn't show any retention. And the bare silica had too much retention. So basically the whole material would not come off under those conditions. So we're looking at these conditions, and we are always looking into the large scale applicability of this process. So we are not introducing solvents or anything that would change the process significantly or make it more expensive, basically. So here you see basically the results. One key parameter in chromatography is the so-called selectivity, where you compare retention times of your target molecules and you normalize them, like here. It's fairly simple. And then you see how well those peaks or how well your compounds are eluting apart from each other. So you basically want the selectivity to be as high as possible, at least bigger at 1.2 actually. So as you can see, you have here different values. The C18 didn't separate, C8 did separate a little bit, NH2 also a little bit, and the diol basically best. So then we always need to play a little bit around with the physical process parameters. So here we have the example with the C8. So you see everything is eluting very fast. So we are slowing down the process to see whether when the compound has more time to interact with the stationary phase, we get a better separation. It looks a little bit better, but if you put your math onto it, it actually stays the same. So we have the same selectivity. So this way this process doesn't improve. And it's important to notice because it looks better, but it actually isn't. It just uses more process time and more solvent. So we are not doing that. So then we looked further into amino and diol. And obviously, as we already thought, the diol surface has the right intermediate hydrophobicity versus hydrophilicity to have the interaction for those acid esters. And you have actually a very good selectivity here of 1.72. And we reconfirmed these results with the original crude oil. So we were very happy. And if we are happy also, the process owner was very happy. So the process is faster and it has a better selectivity. So they can actually have more runs in shorter time and have a higher throughput. So they're gonna switch to the diol instead of the amino phase they used it before. And yeah, one poor take-home message from this was always check your parameters and not just look at shiny graphs. The next example is a reversed phase process optimization of cannabinoids. That's a very hot topic, at least in Switzerland. So we worked together with a cannabinoid producer And they're extracting those cannabinoids from natural plants. So it's an extraction process, and then they purify it. And again, they want to have pharma grade separated cannabinoids. And again, we see how similar they all are. And we need to have 99% plus purity of those. And usually the problem with all those natural products, they're harvested, they have different conditions when growing. Maybe it's a different type of plant, so the concentrations are always different. Maybe you have also pesticides in it. So the purification at the end to really have a high quality product is crucial. We actually published this in the renowned Journal of Cannabis Science and Technology. So what did we do? We had the process conditions. We know it's reversed phase because the solvent is, the mobile phase is already defined. It's ethanol with water. So we can only work in reversed phase. So we checked out all those reversed phase silica gels, mainly C8 and C18. And we realized that the more hydrophobic, the better. So we stick with C18. And then we go through all the physical process optimization. So first we optimize the gradient, the so-called gradient. This is how you put the mobile phase together. So you have ethanol, but you can also add water, but you cannot add too much water because then you have precipitation of your compounds or your analytes. So you want to be at a certain concentration, a minimum concentration, and then we had all those different screenings, but the best was actually isocratic at 70% ethanol. And then we also looked into how we can inject the material. There are different ways of injecting it, and we tried that. It didn't have much effect, also mainly because isocratic is best. So isocratic means we have a constant concentration of ethanol water in this mixture. And then we did a flow rate optimization. This is basically taking into account all those fluid dynamic effects with a diffusion, mass transfer, and alongside the column and also in the axial direction. And there you have different diffusions that counteract with each other, and you always get a sweet spot here with the highest resolution of your separation. And this is what we wanted to get. So then we decided on a certain velocity or a certain flow rate, and then you can adjust your injection volume according to that. And this is what we got. So we have a very small silica particles with a 10 nanometer pore size. So a certain amount of surface area around like 500 square meter per gram, and the C18 on the surface. And then we could separate the CBD very nicely from everything else, also in front of the CBD and afterwards. And what was very nice to see that we actually could separate different THC isomers, because they are also very different in how they act and also on their potency. So you want to separate them if you want to use them in the pharmaceutical application. So again, very happy collaborator. We had a successful process optimization at all those given constraints, because we didn't want again to impose any more investments. We got over an 80% yield of a CBD with 99% purity, and we also got basically 60% yield of higher THC purity isomers. So what I wanted to emphasize is, even if people think they have a good chromatographic separation, you can always improve and look at the stationary phase again. So thank you very much for your attention. And again, I would like to thank all my colleagues, especially Dr. Anna Stojanovic, who I'm working very closely, and the whole team at Tvornik, who are producing all these scales, which we work with and optimize all those processes. And then we have some chromatographic experts who are helping us with this. So yeah, thank you.
Victoria, thank you very much for excellent presentation. And now some question for Victoria. If not question, we will continue immediately because we have presentation of Zeochem.
Ah, yeah.
Yeah, this is important. And our colleague had preparation in sauna yesterday.
Pastor, I will give you a short presentation. Introduction to Mr. Petkovic. Ladies and gentlemen, with this, we finish our second session of talks for today. And we now move to the section dedicated to sponsored presentation. I invite Mr. Zoran Petkovic, General Manager of Zeochem Ltd. Zvornik, to address the conference. So let's give a warm welcome to Mr. Petkovic.
Good afternoon. My name is Zoran Petkovic. I'm General Manager of Zeochem DO, which is part of Zeochem Group. Welcome to this conference. Once again, I would like to thank to the faculty of Zvornik for organizing this event and to give us opportunity to, let's say, to show to the world what we are doing and which we are dealing with. Sorry. I'm afraid I will not be that much interesting as every previous and next speakers because I'm not scientist. I'm just stupid manager, you know. So, but nevertheless, I will try to be as much as possible interesting. So, the Zeochem, I will just start this presentation with our mother. The Zeochem is one of the companies which are integrated in the CPH holding, which is Chemie and Papier holding from Switzerland. It's a, how to say, rather big holding, which is dealing with many different things, among which there is also a chemistry. And as such, the chemistry is under the hub or group of Zeochem. I will not talk much about the other businesses, but I will just mention them. The other businesses are paper industry, in which we are recycling more than 500,000 tons of paper per year, for example, just to mention sustainability, because it's very important in this world. Yeah. As a holding, last year we had a sales of 725 million of Swiss francs, which is approximately the same as euros. And I'm not scientist, but this EBITDA, it's equity before interest, taxes, depreciation, and things like that, amortization. And this is like how much we have gained the money or how much we have earned, or EBIT. It's 131 million of Swiss francs last year, which is not that bad for a small company. Yeah. Sorry? Well, we can do better. Yeah, I'm sure that we can do better. Yeah. So our mother or CPH holding has a website on which you can see all these details, because everything is published in our yearly reports. As I mentioned, paper division, just as a different or one of the divisions, generates lots of money in the group. So last year we had 384 million of francs sales, and as I mentioned, more than 500,000 tons of paper is recycled in our factories. Just to mention, every single sheet of paper which we are producing is actually now recycled paper. No paper is produced from trees ever. As for packaging division, we are usually dealing with packaging of pharmaceuticals. We are making blister packaging, how they call them. And as you can see, the sales last year was 231 million euros. Not bad also. Last but not least is the Zeochem, or chemical chemistry division in the group. We are not that big as our sisters. So last year we had just a net sales of 110 million of euros, and the equity was very, very low. That's 19 million euros, that's not much. But nevertheless, yeah, the chemistry is very important for us, and we are growing and developing every day, every year. And this map shows in which countries only the Zeochem has its own production facilities. So the colleagues which have spoken before me, fortunately not as beautiful as I am, but nevertheless, they are coming from Switzerland, and over there we are producing lots of interesting materials related to Deutero products and related to silica gels. In the United States and China and Bosnia and Herzegovina and Singapore, we are producing different type of products, mainly zeolites and mainly products related to silica gels, which my colleague have mentioned just before me. So these are the production sites which I just mentioned, and in general, we are dealing with production of molecular sieves, specialty zeolites, chromatography gels, and deuterated products. As for the molecular sieves, mainly we are producing or processing the products related to the zeolites 3A, 4A, 5A, and 13X zeolites, which we are producing in powdered shape or in beaded shape. Some of these products are, of course, produced in Bosnia, and some of them produced in China or in the United States. I will not talk much about this, but in any case, applications are very various, from energy, pharmaceutical industry, whatever. Specialty zeolites, what we are dealing with is usually adsorption. So specialty zeolites are used for the removal of VOCs, for example. And for this purpose, we are usually producing the ZSM5 zeolites and mordanite zeolites in different silica to alumina ratio, things like that, but many products. Yeah, applications are also various. One of the famous applications now has been the usage of purification of oxygen, which was very useful for this crisis with Corona. Chromatography gels, I will not speak so much about this because my colleagues have already mentioned everything about this. They have not mentioned the deuterated molecules, but nevertheless, I will just mention that we are also producing deuterated molecules in Switzerland. This is very interesting technology, and it, as from the manager perspective, very interesting because it brings lots of money. As I mentioned, I'm coming from Zvornik. I will just speak a little bit about Zvornik. The production, as my colleague Anna mentioned, for silica gels, for example, was before 2016 was in Switzerland. Due to some matters, the management decided to move this production elsewhere, and one of the options was Bosnia because of the proximity of alumina, with whom we have already cooperated on the synthesis of some zeolites, and from whom we are buying, or at that time we're buying some raw materials also. So we made agreement with alumina to share with them, with a special agreement, to share with them technology and the know-how, and we made with them a factory in which we are synthesizing silica gel and zeolites, and this is joint project with alumina, and we are obligated to buy everything what alumina produces in this factory, and they cannot sell to anybody else anything what they are producing. It's a special frame agreement. Beside this, we have founded separate company. This is just a picture from the project. At that time, I was a project manager for erecting this factory. Actually, when I look at that time and now, I can say that it's not the same person. This is a different person. I'm not the same person, which is, yeah, much thing has shown. Yeah, it's much, but anyway, yeah. Okay, so this just few picture how we can We started to build this company in Zvornik, groundbreaking ceremony, alumni is beside this. You can see the chimneys. This is my manager, just for example. Okay, so in 2017 we had a groundbreaking ceremony in March 6th. In 2018, 1 year after that, the factory was completely built up and already running for a couple months. And as a reward, I have became a general manager of this company. Thank you. Yeah, and you can see some famous people here. This is me, although not that beautiful as now. This is President Dodik, always president. At that time was President also. I think that he will be president when I die, but nevertheless, yeah, okay. So this is a production facility, as you can see. This is how the factory looks now. And we have all the certificates for environment, for the quality management. At this moment, we are producing on the technical desiccant line or molecular sieve line, approximately 5,000 tons of products per year. Just to mention that when we have started, we were producing 2,500 tons. So we are expanding. Now we are doubled our capacity. As for the chromatography gels, the situation is the same. We have started with 600 tons after expansion and everything. Now we can reach 1,000 tons, for example. Specialty zeolites, which we call zeoplasms, we have a capacity of about 350 tons per year, depending on the type of the zeolite. We don't have much employees because it's a small company, semi-automated, just 49. But I would like to mention that out of these 49, 19 employees are with a university degree, mainly related to production and research and development. Well, some of the managers are included also here, but not relevant for the production. Managers are usually students. Okay, so just this is what we are producing from the point of promoles, from the point of technical desiccants. We call them promoles. Promole is a abbreviation of polyurethane molecule sieve. This is a 3A molecule sieve, just a few informations about it. 4A applications are various. These are some, as for these molecular sieves. For the specialty zeolites, as I mentioned, the removal of odors or volatile organic compounds. Chromatography gels, the colleagues have mentioned this, different types, things like that. This is all I had to say today. I don't want to bother you anymore. So thank you for your attention. Thank you.
I hope we worked very hard today. Time for lunch. I'm sorry if you agree. And
Yeah, I'm okay with that. I'm okay. No problem. Maybe somebody has some questions to ask, but I'm just want to mention once again, I'm not a scientist. I don't understand half of thing which you have spoke today about.
I have question later, but now.
Let's say I just want to stress the importance of the connection of the science and the industry and society. So yet, let's say manager could be a good link between them. So we need all our science to go to our society, to improve our society, to live better. So it would be, I think, really very, very nice, all these good things that we learn around the Europe, around the world, etc. If we can have these good practices in our place. So let's say to have here also paper, let's say industry for paper recycling would be nice. To separate to the recycled paper here in Bosnia, to get it, and all of these different waste streams and etc. Just this.
Yeah, I agree. One of the reasons why we are here is this recognition of the cooperation of the science and the industry. Unfortunately, all of the managers at the top level of management are usually, as I mentioned, not very bright. And we need the help of science in developing our products. Just for the mentioning, let's say at this moment inside Zeochem, we have like 35 million of Swiss francs investing in some developing projects at this moment. So, I mean, in every moment we are developing and growing. So just at this moment, there are open projects with the value of about 35 million of Swiss francs. And we are, did not mention that we exist for more than 200 years. And for all this time, we are trying to develop with the help of the science. And in some cases, like in the cases of Zeochem and Zvonik, you have a luck that general manager, which I am, is a cousin of the dean. So we just cooperate because of it. Don't mention this.
Yes.
And he owes me some money, so he wants to give me some favor, you know.
Yes.
Yeah. I'm joking, but yeah, I'm joking, of course. But yes, we have recognized this, and most of these people, which I mentioned, 19 educated people, they are coming from this university, from the faculty of Zvonik. And we have, when the company in Zvonik started to work, at that time we didn't have no R&D, nothing for the development. But at this time, because we have plenty of engineers, we are growing and developing, and we have included the faculty because this is where we were born, you know. And we work with the faculty. Professor Cashel was mentioned already on some also projects in improving or developing our products. And this is very lucrative, I can say, cooperation, because we already have good indicators that we are on a good track, you know.
Yes, yes.
And Anna also mentioned we are luckily also there are some applications which are very good, like this clarification of beer or filtration, or clarification of wine, where you can experiment and drink a wine at the same time. It's beautiful. I mean, it's
Yes, yes,
you can
yes.
imagine.
It would be, yes, and I think just a bit, little wider, so
Yeah.
that the whole society
Yeah,
can
we
benefit.
will spread it
Yes.
to Rakia as well. Yeah, we will write it out.
Yes. Okay.
Thank you very much, Mr. Petkovic. Excellent.
Okay.
We will continue later with questions. I hope no question from online participant and no.
le même que Zelensky, mais qui n'a pas voulu insulter la Chine en disant c'est bien que la Chine se meuve, se bouge pour essayer de trouver une solution. Là encore, les limites de la Chine, c'est tout ce qui pourrait finalement remettre en cause la reconquête par Xi Jinping de l'appareil d'État chinois au profit du PC.
Opposant à la réforme des retraites reste déterminée. Plusieurs actions et blocages ont eu lieu depuis ce matin aux abords de Lyon, Strasbourg ou encore Toulouse. On fait le point avec Benjamin Berthaud.
Vous savez qu'on se mobilise contre le plus fort sens démocratie, je fais ça, ouais. Ils sont une poignée à ralentir le trafic. Ces manifestants aux abords de Strasbourg continuent de se mobiliser. Ils n'ont pas perdu l'espoir d'être entendus.
Une loi qui passe à 9 voix près en moins, je pense que c'est un peu pitoyable. Et il y a eu plusieurs lois qui ont été passées comme ça de force et finalement les décrets d'application l'ont mis en place. Donc ça peut être une solution.
L'échec des 2 motions de censure contre le gouvernement a renforcé la détermination des grévistes. Ici, près de Toulouse, l'intersyndicale interdit l'accès à l'usine Airbus. Certains comprennent.
Oui, mais je suis complètement d'accord qu'il faut se mobiliser. C'est avec la mobilisation qu'on peut arriver à obtenir ce qu'on veut.
Et d'autres sont plus agacés.
La forme, un blocage, je suis contre, clairement. Là, moi, je vais au boulot, c'est un peu dérangeant.
Près de 250 manifestants avec un objectif toujours le même.
On n'attend qu'une chose, c'est qu'ils retirent le projet sur les retraites. On ne le laissera pas voler nos vies et notre vie en bonne santé à la retraite.
Devant les grilles de la centrale nucléaire du budget, c'est un blocage complet qui a été décidé. Les grèves
Jeden.
Dear guests, dear participants, we are continuing with the Congress program. I would like to mention once again that this is a hybrid event, meaning that we are having on-site sessions and online sessions. Right now, we are starting with poster sessions, and I want to emphasize that the scientific committee will evaluate both online poster sessions and on-site poster sessions. The committee for evaluation of poster session today counts 3 members. That is today Sanja Armakovic from the Faculty of Sciences, University of Novi Sad, Daniela Rajic from the Faculty of Technology of Zvornik, Republic of Srpska, Bosnia and Herzegovina, and myself, Stevan Armakovic from the Faculty of Sciences, University of Novi Sad. Because we have a really significantly high number of posters, we will firstly evaluate on-site posters, and then we will be evaluating online posters. So it will take some time until we evaluate posters that have been physically present here at the Jahurin in Termak Hotel. So we are firstly going to check those posters, and then we will come back, and then we will watch the presentation of all online posters. All online posters will be evaluated, will be presented for certain amount of time. That will be 30 seconds. 2 by 2 posters will be going on. And during that time, somebody from the audience, from the respected audience, might have a question. Please do feel free to ask questions while the posters are online on the screen. And we will also join the conversation with you, and let us all be free to ask questions and to make this online session and this whole event as interactive as possible. So thank you very much. Now we are going to check the posters that are physically present here. Thank you very much.
Uh,
Ako može kasnije, nije sad. Pa sad sam popio, ali možda bi uveče. Može posle. Može.
Thank you very much for attending poster sessions. Currently, we can see the online poster sessions. So if you have questions, feel free to raise your hands, and then we can ask the questions regarding the posters presented on the screen. Let's make this as interactive as possible. Scientific committee asked a lot of questions for the on-site poster session. Dear guests, dear participants, in front of the organization committee and the scientific committee for poster sessions, I would like to sincerely thank you for attending the poster sessions, for attending both online and on-site poster sessions. The scientific committee had a beautiful role. We checked all of the present submissions and posters, and we are delighted to say that the quality of the science that was presented here was outstanding. And this is something that is supporting the organization committee for their further efforts regarding this conference. So the total number of submissions was 107. Out of that number, 100 posters were present today here. And out of that number, 31 poster was on site. So it was really nice, and it was a really nice experience to check all those posters and learn some new things. What was really encouraging was that the number of young people was really high, and the quality of their presentation was really tremendous. After a detailed analysis of the posters presented, the scientific committee has concluded that the poster named application of crude fungal lacase from Ganoderma species in decolorization of 3-phenylmethane dye crystal violet, authored by Nevena Ilic and other co-authors, should be awarded with the free conference fee for the next conference. So let us taking into account the design of the poster, the quality of the science, and the quality of the presentation of the poster, the scientific community unanimously decided to award this poster. That doesn't mean that other posters were of the less quality, but it is always difficult to make these types of decisions. If we could, we would reward all of the presented posters. So thank you very much. Thank you very much for the high quality discussion of your results. We feel that we learned some new things, and let us thank once again to the organizers for this great event. Oh, yes, yes, just one more quick notice. The authors of the posters that are presented here can now take their posters with them, and that will be all. Yes. Thank you very much.